Gatridi, you are audible.
Shubhendu, Shinjini, shall I start?
Yes, Gatridi, you can start.
Gayatri, we can hear you. You can start.
Good afternoon, everyone. Before we formally begin, I have an announcement to make. We just received a sad news. A retired teacher of our department, Dr. Shwandha Raichaudhuri, has left for her heavenly abode a few days ago. That is on the 28th August 2020. Shwandhadi, as she was known to us, was a person with a dynamic, cordial personality and a wonderful teacher. She served the college for a very long time. Now I propose that we observe a minute's silence to pay homage to her memory. So I think we can continue now. Respected faculty members from different colleges and universities, the resource persons of this workshop, Dr. Sandeep Ghugre, Dr. Nilatri Banerjee, Dr. Shubhendu Chandra, research scholars from different universities, my colleagues and my dear students. On behalf of the chief patron of this workshop, our principal madam, Dr. Nivedita Chakraborty, and the members of the organizing committee, it is my privilege to welcome you all to this two-day web-based international workshop on Arduino and other simulated experimental techniques. The world in general, and India in particular, is passing through a very challenging time. Never before in our lives have we had such unprecedented circumstances. To keep the academic community engaged in the process of teaching and learning, various web-based workshops and webinars are being organized by different institutions. As our contribution to this initiative, we decided to organize this workshop on various simulated experimental techniques in the virtual platform. This workshop will shed light on the following topics. Arduino, which has recently been introduced in the UG syllabus. It will be an introduction to this open source electronic prototyping platform for our student participants as well as for many faculty members as well. Magnetism and Object Oriented Magnetic Framework is a finite difference program which is widely used to predict magnetism at submicron level. This presentation will give us an interesting insight into the research and simulation done in this field. Circuit Maker 2000 is a simulation software that can be used for design and fabrication of electrical and electronic circuits, which are included in the theoretical as well as practical syllabi of different universities. We hope that our students who were unable to attend classes for the last few months will surely find this mode of demonstration interesting, and it will also be beneficial for them. I would like to mention here that we, the Department of Physics, Victoria Institution College, in collaboration with UGC DA Consortium for Scientific Research, Kolkata Center, had organized a workshop on Python programming in the month of July. That was an overwhelming success, and we had received requests from some of the participants for arranging a workshop on Arduino. So we hope we have been able to honor these requests. We look forward to your active participation in this two-day workshop, and thank you for showing interest to attend this workshop. Now we begin with the technical session directly. The speaker for the first technical session is Dr. Sandeep Ghugre from the UGC DA Consortium, and he was topic. This will be his first presentation and continue tomorrow. A brief introduction to Dr. Sandeep Ghugre is a senior scientist and the head of the nuclear physics group at the UGC DA Consortium for Scientific Research, Kolkata Center. He leads an experimental nuclear physics group comprising of several PhD students and colleagues from different universities and institutions whose area of interest involve in-beam, gamma ray spectroscopy, nuclear structure studies, nuclear instrumentation, detector simulation, etc. Dr. Ghugre did his PhD at the University of Mumbai and his postdoctoral research at the University of Notre Dame in USA. He has to his credit a large number of publications in reputed international journals. In addition to his research work, Dr. Ghugre has been instrumental and the driving force behind the UGC DA Consortium Kolkata Center's initiative in developing a range of low-cost, innovative teaching tools based on routinely available resources for the undergraduate students. He has successfully hosted workshops in collaboration with different colleges and universities across the country to popularize these teaching tools. Dr. Ghugre has developed various codes in Python, keeping in mind the UG and PG syllabi of different universities. His presentation of these Python programs, along with the relevant theory in the 5-day workshop on Python programming, which was held in July 2020, was hugely appreciated and was extremely beneficial for the student community as well as faculty members. We are honored to have him here as a resource person. Now I shall invite Dr. Sandeep Ghugre to give his presentation on Arduino and its application.
Thanks, Dr. Gayatri. Am I audible? Hello, am I audible?
Yes, sir. Yes, sir. Continue.
Yes, sir. Yes, sir. Thanks a lot, Dr. Gayatri. And after such a nice introduction, I hope I can do justice to the good words that she has said. Of course, she missed a couple of points. That when I joined the Kolkata Center, she was my lab mate in the next lab, and I see Dr. Nihar Mishra also join in, who actually shared the lab with me until they both decided I was a pain in the neck and decided to throw me out into the computer group. So it's nice to see old colleagues come in and join us today. We also have Dr. Dinesh from National College, who was the resource person for one of such workshops we organized with the National College in February, just before we hit the lockdown. So it's nice to see the entire family being preserved as we move ahead in these difficult times. So with these words, let's get down to business, and we'll start the thing. Just give me a minute. Okay. So as I said, is the screen visible?
Yes, sir.
Okay. Thanks. So as I said, today back in Maharashtra, I think we bid farewell to Lord Ganesh, whom we all consider to be the Lord of Wisdom. And I'm sure given this pandemic, he must be wishing that the only way forward is to keep on doing things within the constraints and to dwell upon the various nuances of sciences. And no better thing than doing experiments within the limited resources. As I said, most of the things would be simulation, but what I'll try to talk to you about is within very limited resources which are available online. And my constraint in designing these experiments today has been I have purchased each and every component that I'll be presenting today online in this pandemic. So it is possible that we still continue forward in a march or on the, as I said, I am reminded of the famous words by the poet Robert Frost. I took the road less traveled, and that's all that has made the difference. So we would try to search for challenges, opportunities in all adverse conditions, and as Lord Ganesh would wish us, who's the Vignaharta, success over all these difficulties. So let me try to talk to you about some of the experiments that can be done. Budget is roughly less than 1,000 rupees, which I believe when Gayatri told you that I did my PhD, my fellowship was about 1,200 rupees. So that's how we have progressed to, I think, a fellowship which run much more, and $1,000 here and there, I'm sure would be a beneficial investment. So that because finally science is experimentation, and unless you start doing experiments, we will try to do even a simple experiment teaches you a lot more than pages of marking up equations. So that's what would be my take on this kind of a presentation, which I'll do is I'll try to talk to you about some of the experiments, very simple, but if you do them slightly differently, it opens up an entire whole new world. I don't mean to say that we would be innovative experiments when it comes to our mind. We always think of big things. No, innovation means doing the same thing slightly differently and take a road less traveled, and that's what would have made the difference. As I said, the participants can ask questions on the chat box, and I'm sure the organizers will patch you up with me. And in case there is some speed mismatch between my delivery, because this I'm talking to an invisible audience, which slightly makes us uncomfortable. But I guess this is going to be the style of all the things to go on online. So maybe we both have to get used to not seeing each other, which of course has its advantages as well as the disadvantages. So as I said, as Gayatri has said, we had a workshop on Python. But actually the whole thing started was we at the Calcutta Center of the consortium went into the process of developing a range of innovative, low-cost experiments which are based on routinely available resources. You can buy them on all online platforms. You're not limited to a particular vendor. So of course, open source opens up the entire market and without draining out your pocket. We try to take care that the experiments have to be illustrative and should contribute to India's understanding of the subject. So whenever we talk of any experiment, I think the major bottleneck is how do I acquire the data or the data acquisition system? So our 2 cents worth of solution to this was because I need to take this data acquisition system to the house. Or if I'm talking to educational people, I would have said, I want to expand the education ecosystem and have a technologically enabled education ecosystem. In simple language, all it means is the student should be able to do the experiments sitting in the comfort of his home, which all the more is important now given the present day pandemic. So what we found out was the sound card in the PC and a microcontroller are the best. Of course, each one of them has its own strong points. One over the other is, there's no point in discussing one over the other, but it's always one with the other. For example, the sound card really cannot accept DC pulses. We do try to fool it around, but on the other hand, the Arduino is a one versatile microcontroller. I'll come to it. What do you mean by, you'll hear the word microcontroller several times. So let's try to set at rest what is micro and what do we control with it. So these were the 2 data acquisition systems. And once we had the data, we needed to analyze the data. And that's when we actually got into Octave, the poor man's MATLAB, and Python, which helped us analyze the data. And then it opened up an entire new avenue where we went into Python for teaching quantum mechanics, mathematical methods, whatnot, and what for. But our first effort or our first love of a truly experimental person is doing an experiment. And that's what we started off with, which has now snowballed into something which has really not taken us away. But yes, these kind of experiments rarely get talked about. So as I said, the first question to any of us would be, what is a microcontroller? So microcontroller is nothing but a hardware real estate which has everything that you need to do an experiment or record the data. It's kind of a self-contained system with a processor, which of course is the main brain of the entire system, or the CPU, what I would talk about. It has memory, an onboard ROM and RAM, so you can program it, leave it on for, and do your experiment. And most important, it has a host of peripherals, because a computer as such is not useful in your lab unless you are able to interface real world signals into it. So you have a microcontroller which allows you to do the best of both worlds, and it has become absolutely cheap. About a decade back, when I bought my first microcontroller, it cost me around 2,000 rupees. It was about a decade back. Today, the cost has come down by a factor of 10. So that's what is the kind of advancement in technology vis-a-vis the drop in prices. So it really makes it affordable for everybody to have one. And the most important thing is, once you have the data acquisition system to yourself, peripherals which cost absolutely, as I said, each of them would not be costing more than $100. So you can start, it opens you up to doing really open-ended experiments, the same experiments you do in your laboratory. I'm not going to be talking about some hi-fi systems or kind of jazzy jargon, but the same experiments you do in your day-to-day laboratory, you can do it at home. So you can look at the experiment, understand the nuances, the nitty-gritties, and try to do things a bit different. So, as I said, now here is the question, because every time we talk about microcontrollers, we end up with people saying, oh, there is a group from somewhere who has done this, and they have this kind of a very nice system which is built. But what we felt was, either you buy things from Ambala, of course, I'm not using it in a derogatory sense, but you buy something from this. Am I audible?
Yes, sir.
Yes, sir.
Because Gayatri, okay.
Yes, you are audible. I'm taking the questions. Yes.
Okay, thanks. So as I said, we decided that why do I go in for Arduino? Most of the time we hear this question, oh, there is this microcontroller kit which costs around 3,000 rupees, everything is there. but you are a slave to the entire system. Now it has changed from having those voltmeters and ammeters and then trying to go it into micro. So what we thought was, we really need to use the power of open source. I need to have the choice to integrate, assemble, or experiment using very limited resources that I may have. I personally really have been ages since I have done any soldering myself. And for soldering, I have my colleague, Mr. Mukesh Kumar, who helps me with that. But I do not want this to be a limitation to the students. So I have set ourselves a task that I'll use an open source hardware, which is it's a truly open source in the terms of hardware and software. The hardware is cheap. As I said, you get an entire microcontroller. You can get only the microcontroller, assemble it yourself at absolutely peanuts cost to say today. It is, the Arduino is truly an open source. It can be powered either from a USB or a standalone DC supply. And most important, it can run as a standalone poor man's computer, which has a decent memory. And most important, as I said, even in our present day world, we do have a problem with communication. It is always the communication which is the problem, as we have seen in human society. And Arduino allows us to communicate with it serially, with a Bluetooth, Ethernet, so on and so forth. So it's really a robust system. And most important is, as I said, it opens up, it actually connects to the entire world seamlessly. And people who have done microcontrollers, many of us who come from the age-old 8035 or 8085 and 8051 or the latest microcontrollers know it is a pain in the neck to program a microcontroller. You need to write your code, convert it into hex, burn it on into EEPROM. This entire loading of the program takes away all the energy and effort. But I'll show you that using Arduino and an integrated developmental environment, everything is just literally a click of a button or a mouse, as the present day community would say. And the advantage of using Arduino is it works with both digital and analog signals. It has a host available and sensors such as pressure, temperature, whatever you name it, and it is there. And the most important thing is you have various shields or ready-made boards. The shield is a board in a sense which can be plugged on to the top of the Arduino or its variants. I will come to it what I mean by variants, and it enhances its capability. As I told you, you will have an Arduino board. You put an Ethernet shield onto it, and you have your microcontroller on the digital highway. You get ready-made boards which have sensors such as IR transmitter, receiver, ultrasonic distance measurement, temperature measurement, pressure, and in a jiffy, you are able to make your microcontroller talk to the real world. And I said, each one of them at best costs around 100 to 200 rupees. So you can slowly go on increasing your arsenal of the boards and thereby increase the versatility of your experiments. So as I said, how does an Arduino look like? Now, when I talk of Arduino, Arduino is a family. You get a lot of variants of Arduino. And as I said, I personally have worked with UNO, which is I guess there was one of the earlier generations where my variants of the Arduino, but it does it's more than sufficient for us to do most of our experiments. You have something which is known as a Mega. So I have really gone with Arduino, then UNO. For this particular set of experiments, I will use the Arduino UNO. There is a Mega, I'll not talk about it. Recently, they have come up with a variant called the Nano, but it will be difficult for us to support that in the present workshop. because it has slight complications because the original nano is not available. So you get clones, and with clones you really have a problem because they put in a lot of non-standard things. But as I said, so if you can get an UNO, which typically would cost you anywhere from say 300 to about 400 rupees, clones of course, while the original UNO is still about 1600 the rupees. And unfortunately, almost the original things are really disappearing from the market and has been captured by the clones. So we'll talk about this kind. So this is what a microcontroller would look like. If you walk into a shop in Chandni or maybe Lamington Road in Bombay and ask them to give you an UNO, this is what you would get. The shopkeeper would hand you this. So that's all that you need to get going onto the world of microcontrollers. Of course, you need certain things to use microcontrollers, and there would be certain things which if you have, it will make your life better. So what is absolute essential is, as I said, since I'm talking about the Arduino Uno, you need your conventional USB printer cable. It's the standard cable by which you connect your printer to your computer. Now, so that this is absolutely essential for you to start into the world of microcontrollers. Preferably, what you would like to have is breadboards. Now, in the breadboards, I'll spend a bit of time. You have a mini breadboard and a small breadboard. There's a slight difference between them. Each one, again, has its own importance and relevance in an experiment. It makes our life easy. I personally prefer to use a ready-made breadboard power supply because whenever you are doing any experiments, you need a DC source of power. Again, all the experiments we have set about is we have kept the safety of the experiment of the student as well as the apparatus in mind. So I would never really use the live supply, but would always try to power up all my experiments from a DC supply. And I will show you that a breadboard the power supply, which is again available off the shelf. I got it from either Amazon or Flipkart or any of the online things. It really helps us in a long way. You would need connectors. By connectors, I would say single strand wires. Nowadays, you have fanciful connectors. I'll show you. Having a few of them does make your life very easy. You can have breakout boards. I will show you have a lot of breakout boards which have the input of sensors and they make it compatible to the Arduino. So you suppose you want to measure the temperature, you'll have a breakout board which has a thermistor onto it and it has a proper buffering, cable driving properties so that it can be interfaced directly to the Arduino. And of course, the components would be as per your requirement. So these are the things you will have to have in your kitty before you actually start with the experiment. So, as I said, this would be a small breadboard, this would be a mini breadboard, and this would be a small breadboard. My apologies to the experts, since there are students, the breadboard, if you see something like this, these pins are horizontally connected, the top two, which you see. These are connected vertically. So, in a smaller one, in the mini one, you'll have all these pins connected, all these pins connected. But the entire line is not connected. So you have a break here. So if you wanted to connect an LED, you can put one leg here and the other leg here. So I will use mini to make small experiments, whereas this small breadboard is very helpful when I have to have my power supply onto it and put in small components. Now, most important thing would be, as I told you, I personally prefer this breadboard power supply. This power supply is what you would be looking at. It needs an input power supply, and again, it takes a DC input. So I can connect a 9-volt battery to it, or I can have a USB input. So this will have an input DC supply, which you can power it through your conventional mobile chargers, or you use the 9 volts batteries that we see around. It gives, as I said, whenever you are doing the world of microcontrollers, you need a power supply which is either 5 volts or which is 3.3 volts. Now don't ask me the reason why these were taken, but these are the de facto standards for any microcontroller piece. So basically this power supply gives you 2 such outputs. It will give you a 3.3 or a 5 volts on the lower rail and 3.3 and 5 volts on the upper rail. These are jumper selectable. So if you put the jumper in the first 2, you may get 3.3. If you get in the jumper in the second 2, you may get 5 volts. So depending on your choice, you can have a 3.3 or a 5 volts, which is routinely required for a microcontroller. It has a push to on switch as well. So the moment you connect your input supply, you put it on, you'll have a power indicator, and there you are set to go. Now, so this is how the power supply would be integrated. Now, this power supply can only be integrated into a small breadboard, which I showed you. This would be my breadboard which will be used. So this breadboard has to be used if you were to want to use this breadboard power supply. Next is what we use is the male-to-male connectors and a 9-volt snap connector. So you connect your 9-volt battery here, you have this input, and you can couple a 9-volt battery to this. So the breadboard power supply will have its power derived from here. And of course, we use, these are what in our colleges we would call them single strand wires. So you have a male-to-male connector, you have a female-to-female connector, you will have a male-female connector. So these are routinely available, or a simple single strand wire should do the job. This is what I talked about the breakout boards. So if you see on your microcontroller, let me just go back. You have these kind of devices. So you see, I will come to the nomenclature of these pins later. So, but these really are tedious to access. So what this shield does is, it makes life easy for you. You have brought them out. You can assemble your contacts. You can put in the mini breadboard here and assemble your circuits in a jiffy. This is the prototype shield for Nano. Nano has really saved on the hardware real estate and almost making it difficult to access the pins. So that is why if you are using a Nano, a prototype shield is a must. So if you put in the cost of a Nano and the cost of a shield, it almost works out to be the cost of a standard Arduino Uno board. So therefore, my personal choice of the Arduino family is the Uno, and I've been working with for almost a decade. It has never given me a reason to complain. So this is the Arduino Uno. Before I proceed, are there any questions, doubts, or anything? Gayatri?
No, nothing.
Okay.
Nothing as of now. I'll let you know when there are questions. Okay, you can.
Yeah,
continue.
I thought if there were questions, I could take a break.
No, there aren't any questions.
Yeah, okay. So the Arduino Uno, if you look at it, you'll see something like this. And the heart of any Arduino is what is called the Atmega some number chip. So that's where the entire money lies with it. So it's an Atmega microcontroller chip. So this would be the Arduino Uno is based on this Atmega 328. Now they keep on changing. They have some numbers which I don't understand how do they do it. But that's what it would look like if you wanted to use a Arduino microcontroller. So as I said, it accepts analog signals as well as digital. I should not say it accepts. You are able to handle analog and digital signals. By handling, I mean you can either accept them or you can output a signal in analog or digital form. As I said, many a times I personally do not prefer to use a 9-volt supply, but I like to power the Arduino using this USB connector, because it serves two purposes. It helps us integrate this microcontroller to the host computer on which I will be doing my programming. So I serve the dual purpose of using the USB power as well as the connectivity to the host computer on which I will be doing my programming. It has a power, the LED, just to tell you that the board is alive and kicking. And this is the way you connect the Arduino to your computer. It's just a standard USB cable. You take it off from a USB port and connect it here. And this is my power supply LED. The moment you connect it, you will see that it glows. So it tells you that the board is alive and kicking and you are all set to go. So let's spend some time and look at the hardware real estate. What do we have? So as I told you, the heart of the Arduino is this chip. You can see it's an Atmel chip with some numbers, which I told you. So this is the brain, heart, whatever of the entire microcontroller. Now, having a microcontroller, you need to communicate with it. The communication is done by this chip. This is what old timers would remember. It's called the UART chip, which is a mode of communication in a certain form. Because as I told you, all communications takes place in digital world. So there I have to specify how many number of bits I'm transferring, what does the first bit stand for, what does the second bit stand for, what is the last bit, stop bit, parity bit, all kinds of things. So all these communications are handled by my bit B. Now, this block, which I marked C, is basically, Arduino gives you, it knows that you may want to use other components with it. So it provides you the facility of outputting a 5 volts and a 3.3 volt supply. So if you wanted to power your LED, I would just use this 5 volts power supply. It is decent enough for me to drive most of the apparatus that I would like to handle in the course of our experiments. Now this is the most important part, is the analog pins. So as I told you, microcontroller is, so just before I come to that, as I told you, is that this is the most important chip. It has all kinds of memory, flash memory, RAM, electrically erasable ROM, which helps you store your program. So the heart is that big chip that I showed you. Now, as I told you, I really need to interface signals to it. And that is done by my I/O input output pins. So it is able to accept signals or output a signal to the real world. So therefore, any pin that I use, as I said, we'll be dealing with analog signals, we'll be dealing with digital signals. So I have analog pins. I will also have digital pins. That means these pins can accept digital signals or output a digitally compatible signal. Now, the most important for us would be the analog, because everything in this real world is analog. So all real signals that we deal are analog, and therefore we should have the capacity to handle these analog, or what I would say, continuously varying signals. So the Arduino Uno has 6 analog pins. That means I can accept 6 analog signals simultaneously. So they are labeled as A0 to A5. So I have 6 pins which will help me accept analog signals, with the limitation that they can only accept a maximum voltage of 5 volts. Some of the variants of Arduino accept only 3.3 volts. So you have to take care to ensure that you know what is the maximum level of analog voltage that your board can handle. So Arduino Uno can safely take in a 5 volts of analog signal. Now, as I said, the real world is analog, continuously varying signals. But when the moment I go into the world of computers or microcontrollers, I have to talk in terms of digital things. So I basically need an analog to digital converter. And Arduino Uno has a 10-bit ADC. I will come to it, how it does, and how do we quickly check out the various things using this. And remember, these pins measure only voltage. They have a very high internal resistance, so current is less. So you can only measure voltage and not currents. Similar to your
Can I interrupt you for there are two questions. Ratnadeep, he wants to know little more details about this UART chip.
That is the chip which is used to set up the communication between, it's a UART chip, it is the communication between the microcontroller and the host computer, because you would like to communicate. So all this communication, the synchronization, everything is done by that chip.
Okay, and Prashant Kale, he has a question for you. He says, can we use this Arduino family for designing military grade and medical grade equipments?
If you really see, there is no difference between the military grade and except that they work under most extreme condition. And if things started working under extreme condition for 200 rupees, I think the defense industry would have shut down. So you have to learn that these are basically poor man's electronics. So they are really not designed to work under extreme conditions. Because if you remember your TTL ICs, they come with 7400, and there is something under the two numbers which tells you whether they are normal grade or military grade. And military grade means they work under they are really forgiving as far as your current driving capacity, temperature thing capacity, and as they say, there are no free lunches in the world, the cost goes up. So in principle, yes. In practice, no. Because as I said, the main cost goes into reliability, redundancy, working under strange conditions, and that will drain out quite a lot of your money. Okay?
One more has come up. Mrinal Maiti is saying, how do we measure analog signal which is above 5 volt? In this case, he wants to say.
I will come to that on my last part. You use a voltage divider and you scale it down. That's all. As simple as that.
Okay, thank you. Please continue.
Yeah. So the digital pins are what I'll just come to it. So these are the digital pins which you get. They have certain labelings from the numbers. So they accept and output a digital signal. That's a TTL compatible 5 volt signal. And some of these will have an approximate sign besides them. Those are called those are special digital output connectors where you can get a poor man's analog signal by using, I'll talk about it tomorrow, using the pulse width modulation technique. So I can output an analog signal for using these digital lines. And they have and these are the kind of limitations. They take in about few milliamps of currents is the maximum you can give. So anything that you connect should have at least a minimum 330 volts or a 330 ohms or a 470 ohms current limiting resistor. So when you connect something into it, make sure it comes through and a current limiting resistor, which typically should be about 330 to 470 ohms. You have then the crystal oscillator, which has a 16 million ticks a second. That's the kind of your computational speed. Now, this is the main important thing for Arduino, is what they call the IDE. So as I told you, people who have done microcontroller programming will tell you it's a pain in the neck. You write a program, you then burn it into an hex code. After you have the hex code, you burn it onto an EEPROM and then finally go and load it onto your microcontroller. By that time, you are dead tired. You never know that where you made a mistake if the program works. So microcontrollers never caught on the fancy of a modern lab because of this limitation. And this is exactly the limitation that has been addressed by the IDE. So if you have this IDE, it does everything for you. So it is an intelligent slave for you. And the beauty of this is that you have this available for all flavors of OS. And they are absolutely easy to install on Linux, on Windows, on Mac. In fact, I have personally tried it on almost all variants and they absolutely do not pose any problem. So you can just download this from, of course, there are some sites because as it happens, the Arduino was started by two partners and finally they, as everything ends up in a fight. So you have something which is called Arduino.cc. And I think there's another partner now has broken up and a site arduino.org. But as I said, for us, it really makes no difference. So you can download this integrated development environment from this site. For Windows, you can. I always prefer to use the installer rather than the app. I have never tried the app so far. Now, the moment you have installed it, then you need to configure the environment. So basically, if you are going to use this environment, which needs to know what is the microcontroller board you have. So it needs to tell us, we need, before we can use it for a thing, we need to tell it two things. We need to tell it the board we are using because it has an entire range of boards. So basically, I may use an Arduino Uno, Nano, Mega, whatnot. So that is why I need to tell it what is the board detail I'm using and to which port is my microcontroller connected. The port that is connected is my standard USB port. And the best thing about this software is most of the choices that it will tell you are your correct choice. So you really don't have to break your head about it. So first, let me go back. So first I need to select the board. If you give me a minute, I'll try to connect an Arduino to my computer and maybe that would be better. Give me a minute. Are there any questions, Gayatri? Hello? Hello? Hello?
Real Ghosh, he wants to know, am I audible?
Yeah.
Internal Ghosh, he says, does the Arduino pick up changes in voltage measured by the connected sensor as input?
Pardon, I did not get it.
He says, does the Arduino pick up changes? He says, does the Arduino pick up changes in voltage measured by the connected sensor as input?
Yeah, it will do it because if anything,
that sensor you were talking
like
about.
for instance, I saw when you are doing a charging of a capacitor, the voltage will keep on changing and it just measures. It just measures whatever you give it at the input. Whether it remains steady or not, it really does not give a damn for it. Yeah. Other? So that's.
And one more is, can we use Arduino for phase lock in detection? For Arduino for phase lock in detection.
I do not understand what he means by that because phase lock loop would mean that you really are
phase lock loop.
But then you will have to design all your things because you will have to design a reference signal. You need to.
We have to design the phase lock loop separately.
Okay, so now you see this is how when you click on
so when
you click on this icon, you will get get something. Don't bother about what has come because it was what was stored on it earlier. Now you go is, it will tell you that I have an UNO because it already found that I had connected an Arduino UNO to it. Then I need to go and select the COM port. It will tell you which is the default port it has to connect. So you make sure that you are all these kind. In fact, you have a couple of ports and you have not selected the right one. It will tell you by printing this Arduino UNO that this is the port you should be setting. So once you have told it which board you are using and which port you have connected, you are all set to enter the fascinating world of microcontrollers. So as I told you, you need to configure the board and the port. It will tell you that you need to choose COM9 and not COM4. So if you do it, you're all set to run. Now, as I told you, the major advantage this IDE gives you is that it allows you the flexibility that you write a code in human readable format, and it does all the donkey job for you at the back of your head without you even knowing how much trouble you had to take if this development toolkit was not available. Now, each of the program of Arduino is called a sketch. So when I talk about a sketch, it means a program written for an Arduino. So as I told you, all of us programmers, whenever we learn something new, I would like to say hello world. That is the first program we learn, whether it's C, Pascal, Fortran, C++ or whatever. That's the first program we should know. So basically, the hello world is the program where the program tells the world, hi, I am alive and kicking. So the analogous part of the hello world program in a microcontroller would be that this Arduino microcontroller has a LED connected. The LED is connected to pin number 13. So my hello world would be Arduino links this LED and tells us that it is alive and kicking. So as I told you, because it's a digital pin, how would I make it blink? I would make it high for some time, then make it off, again make it high, again make it off. And remember, this program is so simple, but it is one of the most important or versatile programs, because if you know that something is not working, this is the program you should run and ensure that everything is up and running. So a sketch would basically have two components, a setup and a loop. Now, as the name suggests, so let me try to, so this is how your sketch would look. Now, it has, as I told you, two components. It is a setup. So setup are commands which you want to run only once. You like to initialize certain things. So those commands are run only once. Say now I would like to communicate with the host computer. Now whenever I am doing that, I use a form of communication where it is called setting the baud rate. Where I tell my computer how many bits I am going to transfer, what is the start bit, what is the stop bit, what is the error bit. So all these things need to be told, and they are done by setting a particular speed of transmission. So most of the time, since I need to communicate with the microcontroller, I would be using those commands in the setup. And I'll show you a slight change in this kind of thing will allow you to do very good experiments. And loop is something which you do, which you keep on executing continuously. So what you would do is you will write a sketch, then you will compile it, convert it into a computer readable format, and then you will upload it. So in old days, when people burned their hex codes on the EEPROM, this is done by using the upload. So you write in a sketch, you compile it. If there are any errors, you can set them correct, and then you upload it. So once a sketch has been uploaded onto the computer, onto the microcontroller, even after the microcontroller has been disconnected from the host, it has been powered down and again powered up, that program is retained in its memory. So you can program it for a particular thing, disconnect your computer, leave it at a remote location, and it is all set to go. So that's how a sketch looks. You'll have a setup and you'll have a loop. Now, as I told you, the first program would be blink, where I need to make an LED blink. So what I would like, as I told you, each pin can be used as an input as well as an output. So I would like to define in my setup that I am going to use a pin. As I told you, the onboard LED is connected to pin number 13. This is going to be used as an output pin. Since I'm going to give it a high and a low signal, I define my pin number 13 to be an output. That I'm just not going to read anything onto it, but I'm going to output. So this would be my setup. And then I'm just going to do a digital write. So as I told you, if I'm using an analog pin, which I'll do it in tomorrow, I'll have an analog read or an analog write. So here I will be doing a digital write to my pin, which I defined as 13 and high. That means I give it a 5 volt signal. I sleep for some time. So this delay is an inbuilt command whose parameters tells me 1000 in units of millisecond. So I sleep off for 1 minute. Then I make it low. Again sleep for 1 minute. So I've done a high, low, high, low, high, low. So that's how I have generated a TTL compatible signal. Now this is how you would do it. You will have the code written. Then you will use the compile button and then you will upload it. And during the uploading, since the microcontroller is communicating with the computer, the received and transmitted LEDs will flash. That's how you do it. You write in a sketch, then give the verify compiler. It will say, okay, I have done compiling, how much amount of memory it has used. And then I go for my upload. It will tell you it has done upload. So then you know that you have programmed your microcontroller to do exactly what you want. So as I said, once the code gets uploaded, the LED will blink and you'll see it. Now, let me just show you this. How is it done? Does any of the participants have this the board with them, or Gayatri, can you ask them? Hello?
Yes, just a minute. Yes, the Dr. Gugre would like to know if the participants, do you have a Arduino Uno board? Yes,
So
some
they can
of them
just try it
have.
out, maybe.
They are
Yeah.
saying so in the
So what you do is,
yes,
yeah.
maybe you can try it out simultaneously.
or right, and then we can get back to. So this is how it was done. It is COM port.
Some people have, some
Okay,
don't. Those who
They
don't
can
have, they can
So that's
later
it.
on. Yes. Okay.
Now this is how I'll do. I'll just to make a life simple. I'll put in a S over here, and then what I do is I verify. It immediately told you that there was an error, because many times we have a typo. Right? I correct this. I again compile it.
Actually, the screen is not very clear. So the things are not, the program is not readable actually.
Can you see it now?
For us. Not much,
Okay,
not much
just
of a
hold on.
difference.
I think it will.
Yes, this a little better. A little
Yeah, I
better.
think that's
maybe
the-
if you can
that
give it in the if you can give it in the full screen mode.
I think it is a full screen only. That's all.
Oh, acha, acha.
I have all these in my PPT also, which I will share with them.
Oh,
So-
okay, they can
So
they
the
can
moment-
see it
yeah.
later.
The moment you compile it, then you do an upload. So the moment is upload, and you will see that. I'll just show it in a video. I think I have a video how it will look like. Oh, sorry, this will not be the one. Yeah. So this is my onboard LED. It will keep on blinking, and I have put a symmetric on and off time.
Sir, please maximize the screen.
Yeah. Okay.
Yes, this is better. Yes.
So you see, this is the onboard LED, which is blinking, and I have put in a symmetric on and off time. So that is why you get a symmetric. I can do one more thing. Yeah. What happened? Yeah. What I did was, this is what I did. I connected this digital pin 13 through a current limiting. I had a 470 ohm resistor to an external LED. So I had my pin number 13 being connected via the current limiting resistor to an LED external, and the other end is grounded. So this is the pin number 13, and this was the ground. And you see that both of them are blinking in. So that is the first thing which tells you that your microcontroller is working, you are able to program it, and you are all set to go. Clear? Now I have a question. What kind of an innovative experiments can you design using this simple experiment? Can anybody tell me? What would be the innovative experiment you can design using this simple experiment? Any idea?
Would somebody like to answer? Somebody saying switching circuits, manually controlled robot car.
No, I want innovative experiment.
We can turn on and
Innovative experiment. That's where the catch is.
Turning on and off.
Traffic lights, they are saying.
Oh, उसमें innovation क्या है भाई?
One person, Dinesh, says LED as a counter.
No, the counter तो नहीं है. This is something which we all studied in a high school. Persistence of vision. We all know that if an image lasts on our retina for some time after it is actually gone. So what you can do is you start playing around with the delay. Keep on decreasing it. Till a certain delay, you will see the light being on, off, on, off, on, off. If you decrease the delay below that limit, your eye cannot distinguish between the on and off, and you will see a uniformly illuminated LED. So this is a simple experiment to show you. Of course, we heard that it is, I think, 1/10 or 1/16 of a second. Here it will turn out to be around 22 milliseconds or something like that. You can try it out actually. So this simple on-off experiment can tell you about persistence of vision. That if you decrease the delay below, I think 60, that's our 60 milliseconds or something. I keep on forgetting the number. You will see a uniformly lit LED, and that tells you that our eye is insensitive or cannot distinguish between the on and off, because they happen within the time duration of the persistence of vision. That's what I told you. These are very simple experiments, but you can try to keep on doing, do some little bit change. That they tell you a lot about the experiment. So as I said, you have done this. Now we will come to something which is very important, which is called the analog to digital converter. Because all signals in real world are analog, so they take a continuous value between 0 and a certain upper limit. In the present case, it goes from 0 to 5 volts. Now, the moment you have given, and the ADC that we have is a 10-bit ADC. So what do I mean by 10-bit the ADC? Given a voltage between Vmin and Vmax, it will map it to, as I told you, I have a 10-bit ADC, it will map it to 2 raised to 10 digital numbers. So it will, what it will do is, as I told you, my ADC, now remember one thing, ADC will always give me a digital number corresponding to a particular analog voltage. And what we do is, depending on the bits of the ADC, it will map Vmin to Vmax to 2 power number of bits digital number. So 2 power 10 would map it to 1024 digital numbers, which would mean we have a 1K ADC. So whenever you hear people say, I have a 1K ADC, it means it can map Vmin to Vmax to 2 power 10 so many digital numbers. And if I was talking to a person on the street who is not a technical person, I will tell him ADC केला बेचने का काम करता है. 1 banana costs 1 rupee, 2 bananas will cost 2 rupees, 5 bananas will cost 5 rupees. That is what an ADC does. Just map my from Vmin to Vmax according to the number of bits. That is what is how an ADC works. So basically what I have to do is, whatever is connected to my analog input is converted into a digital number, which I have to map it into what I had given. So maybe I'll stop here and take it off from this point where we'll do how do we calibrate. Now, if I want to give a technical jargon, I'll say I want to calibrate it, I want to map it, I want to do a energy calibration kind of what basically I'm doing is I am selling bananas. 1 banana costs 1 rupee. So I know that V minimum in my Arduino case is 0, will correspond to a 0 digital number. V max, which is 5 volts, will correspond to 1024 or 1023. I keep on forgetting that depending on where you have started. So V min equal to 0 is the first channel. V max equal to 5 is equal to 1023. So using the good old unitary method which we run, we can convert or map the things from ADC channel numbers to the real world. I'll talk about it maybe tomorrow. As I said, it appears complicated, but it is our good old unitary. Gayatri, I have come to an end.
Yes, no more questions, but some people were coming out with innovative ideas, like you were saying. Somebody said you can use it for a Morse code, then square wave generation.
Exactly.
I mean,
exactly.
people could try it.
Yeah, that's what I just want people to think. But as I told you, this on and off experiment, best way would be you keep on changing the delay and see when the LED is uniformly lit. That tells you your response time of your eye to distinguish different. I guess I'll stop here and then start from this part.
Any more questions from the participants for Dr. Ghugre?
And if people have these boards, they can try it out, and maybe we can start from here tomorrow.
Well, if there are no more questions, I'll thank you, Dr. Ghugre, for your fine presentation. I think we'll stop here for a few minutes and then start with the second technical session.
Thanks, Gayatri. I think I have stopped my presenting, right? My presentation?
Yes, you have. Okay, there.
Yes, sir.
Now one question has come.
There is one question, Gayatri.
Yes. how can you blink two LEDs simultaneously without any time delay?
Two LEDs simultaneously means you connect the LEDs to pin number 13, pin number 12, and just you have that code there.
And the experiment which you were showing, I think there was no time delay. It was
No, there was a time delay of
without-
1000. It was there.
Okay, it was there. Yes.
Ah.
And can we generate a pure sine wave? Can we generate a pure sine wave from our Arduino experiment?
Yeah, it is possible, but then you have to load all the sine wave values into an array and then keep on recalling them. It is possible, but it is not trivial. Hello?
Yes, yes.
Yeah, it is possible. You will have to load. There are ways you can actually load it. You have a table which gives you the values of sine at various points, and then you just output it. It has been done, but as I said, it's not really the best way to do it.
Okay, any more questions? Let me see. Then one more has come up.
Yeah,
Then can we use it as a log
I
amplifier?
have absolutely no idea what it means, and I have never done it myself, so I will not be able to answer it. As I said, my own limitation with Arduino has been to design these experiments. I have never really gone beyond a classroom demo. So maybe it is possible, maybe not. It is possible to use any high-level language to program the microcontroller. You can do it in Python. Definitely, you can do it in Octave. Definitely, if that's what you want.
Yes.
You can do it in C, but then you will have to write all your device drivers yourself. Because the main thing is you need to communicate to the microcontroller, burn the hex code, do all these kind of things. And when it is available to you something so readily, I really don't think it would be worthwhile spending the time. But if somebody wants to do it, it can be done. But as far as high-level languages, C, it can be done. You'll need to load in all the device drivers, etc., and it is not trivial. But Python and Octave, it is slightly easier to do it. Python is not supported in Arduino. You have to write your Python programming. If you see in my last Python book, I said you need something called PYCDL. So using that, it is possible to do to program everything in Python this time, but I'm not going into it. But if somebody wants all the programs that we'll be doing it, I have converted into an equivalent Python code, which if they want, they can write to me. I will share them with them. Okay, thanks. I think next is Shubhendu Da.
Okay.
You can take a break.
Yes, thank you, Dr. Ghugre. Shubhendu, shall we start or
I can start.
you can start? Okay. Then let me introduce you formally. So after the first lecture on Arduino and its application, we move over to the second presentation of the day. The speaker for the second technical session is Dr. Shubhendu Chandra. He'll be talking to us on Circuit Maker 2000, demonstration of virtual electrical and electronic experiments. And today he'll be mainly talking about analog circuits, and tomorrow he'll be talking about on digital circuits. A brief introduction to my colleague, Dr. Shubhendu Chandra. Hello. Dr. Shubhendu Chandra has secured MSc degree in physics from University of Calcutta in 1998. He is presently working as assistant professor in the Department of Physics at Victoria Institution College under the University of Calcutta since 2007. He is also the head of our department as of now. He got his PhD degree from Jadavpur University in 2018. He has published many research articles in international reputed journals in the field of Raman spectroscopy, particularly His interest is on surface enhanced Raman spectroscopy, that is SIRS in short. So now I'll request Dr. Chandra to give his presentation.
Thank you, Gayatri. So good afternoon, all of you. I am Dr. Subhendu Chandra, head of the Department of Physics, Victoria Institution College. Very much glad to represent myself as a resource person in this web-based international workshop. Circuit Maker is actually a high-level simulating software by which we can simulate various electrical and electronic experiments in UG and PG level virtually. It will cover a wide area of sophisticated analog and digital experiments. The Circuit Maker 2000 is completely freely available. It is very easy to download. Download it and install its standard version. Its professional version probably not free, but standard version is sufficient for our exposure. If we are able to install the software that I provide you, the process of downloading and its installation, then you can use it very easily. I think in this pandemic situation, the students are unable to attend the practical classes in reality, and it is very much helpful to realize the electrical and electronic, both analog and digital circuits, practically in virtual field. So now I am starting with a very easy circuit. Now I am sharing it. Gayatri, can my presentation is visible?
Yes. Yes, but if you go to the full screen mode, it will be better. Full screen.
Full screen, it is actually in full screen mode.
Okay, the screen is a little small, so if you can expand it a little more. Yes, that is.
Is this a full screen mode or not? Gayatri?
No, it is a little small. I think, but you are in full screen mode only.
No. I am presenting in full screen mode. No, stop presenting now. Then present now. Entire screen. And then this is the full screen mode. Okay.
Yes, this is better. This is better.
So now I am
a little
starting
better, yes.
with a very simple circuit. This is the Circuit Maker 2000, and in the left hand side of the screen there are so many icons are there. Icons means there are so many equipment, in electronic and electrical equipments are there in the left hand side. So first we'll start with the general. With the general BJT, capacitors, diode, inductors, etc. So first we'll start with the resistors. So resistors, this is actually resistors, resistor A, there's so many resistors and the different types of resistors are there. Here we click, single click and place, and we get a resistance, and in full screen mode, this is the resistance. Okay. So now, if we just another resistance, so you can just right click on it and duplicate. Okay. So another resistance here, and you place it, and like this. Then you go to the source. It is oriented in alphabetically. So it is go to the source. So your source, then we linear source. So linear source, one is battery is here. So place the battery here, and then a ground. So in analog circuit, we must have to place a ground. Otherwise, the circuit cannot be simulated. So this is very easy circuit. But if we want to change the aspect ratio, then we have to go the display scale. So this is 980 aspect ratio. So we will just 300 aspect ratio. Then we get a small picture or the small circuit diagram. So we connect with the help of these wire tools here, and we connect it very simple way. Just connect. And if we want to displace the ground, then like this, and then connect with the battery, and the battery negative is connected with the ground. So this is a simple circuit. So now is simulation. Simulation is in the analog mode, and then run. So if you want to show the full screen mode, only the circuit, then this port you have to click this, the schematic view. And if we only see the graph only, so this portion, and graph and electrical circuits both are present in the circuit, and up and down portion, and this is actually left and right. So now here the operating point, you have here operating point. What is the voltage? Voltage can be shown in the 5 volt, because the two resistance are the same. So if you want to change the resistance, so double click on it and just 500, right? 500. So this is the 500 ohm, and this is 1K. So if we just want to show the voltage, just click on the wire. So if we want to measure the current, then we have to press at the end of the resistance. Then we'll get the current. 6.667 milliampere, like that. Okay. So if we want to see the power, then we have to just click on the resistance. This is the power. So power is 44.44 milliwatt, like that. Okay. So if we now simulate the circuit, then we have to have complete like in the view portion option simulation. So go to the analysis setup, and the DC. This is the DC circuit. So go to the DC, and we apply only one voltage source. So here only the V1, only the voltage source. If we apply the two voltage source, then V1 and V2 are there. Depending upon the characteristics curve, we have to apply it is primary or it is secondary. So we'll find out later. So now the voltage is like 10 volt. So start value is 0, top value is 10, and the step value is 1. That is one step by step it will act. So okay, then run analysis. So here we see that DC sweep and operating point. Operating point by default it is coming, but this is for the DC sweep we have to perform the previous simulating procedure. So now the DC sweep, we just click on it. So this is the car. It is on the screen, in the right side of the screen. This is the car. So if we want to do the car, and for the another resistance, just shift it and click on it. If the another car will get. Okay. So if we just show this car with the full screen mode, we have to go to this icon, and then if we want to choose of the different points by which we can measure the current and voltages, then give the right click and scaling. Right click and scaling, or give the right click or reference. For the reference scale, I will show the designation symbols, data points, bold waveforms, and etc. So we get the data point. So how can we measure the data point? So we go here from the measurement cursor, R1, and this is also for R1. This is for R1 resistance. So if we just change this, the only R1 is available in the screen. So this value actually will be in the x-axis is 3.92 and y-axis 3.9. Same. So if we want to analyze the value of the curve, which is in the below the green car. So we can consider the second like this. The second cursor is coming, and the second cursor is going to the different points, and you can measure accordingly. Okay. So now just stop the simulation. Now if you want to simulate the circuit for the current, this is voltage and voltage. For the voltage and current, so for the voltage and current, we have to just click on it. That is at the end of the resistor. So this is the milliampere current, this is the voltage. Okay. So if we want to measure the current for the another, the same curve, because in the series circuit. In the similar way, if we want to construct a parallel circuit, so you can just duplicate coming here. So for the rotation, this is 90-degree rotation. This is also for 90-degree rotation. We will get a parallel circuit, and you just connect like this. This. This is the parallel circuit. So for if we just change the resistance, this is actually 200 ohm. 200 ohm. So if one can analyze the circuit, then the voltage will be the same, 10 volt. If you want to measure the current will be minus 50, that is 50 milliampere, and this is also the 20 milliampere. So for low resistance, more current. So now if we analyze this circuit, simulate this DC sweep, and for this current and this current, there are two different currents. Okay. So now this is simple circuit. So now we just want to come another circuit. So now open. New. Yes. So if we just cross it and no. If we implement a circuit like series LCR circuit, so LCR, so this is for general. Here is inductor, capacitor here, place here, then inductor here, place here, LC, and then R. R is the resistance here, place the resistance. Okay, so full screen mode. If we want to change the value, so like this is 100 millihenry, so 100 image. We want to change, this is actually 1 microfarad. So if we just want to change 0.1 microfarad, 0.1 microfarad, and this is actually 100 ohm. 100 ohm. Yeah. So with a source, AC source, you have to go to the instrument section. Instrument, this is actually in the alphabetic order. Instrument, analog instrument. This is signal generator. This is the signal generator. It plays here. So now give, then display scale. We just use some 200 display scale. So if we just shift this resistance, inductance, capacitor, and then connect it with the signal, like in very simple way. So if we just run it, then it show error because ground is not connected here. So we have to connect the ground. So ground section is in the actually source, linear source, the ground, place here, ground, then we connect. Okay. So this is actually 1 kilohertz, and 1 minus 1 to plus 1 means the voltage, the peak to peak voltage is actually minus 1 to plus 1 and 100 kilohertz, 1 kilohertz. If you want to change the frequency, just you can go here and 1 volt, 1 kilohertz, and like that. Okay. So now, if we want to measure the voltage, so what is the voltage across this? This is actually the input voltage which is applied. Actually, 1 volt, peak to peak is 1 volt. 1 volt. Okay. So now, if we want to the voltage across this point, actually the voltage across this point, actually voltage measured from the capacitor as well as the resistor. This is always measured with respect to the ground. This is the input. This is the measuring from here, means the voltage across capacitor as well as the resistor. So if you want to measure the voltage across resistor, then we measure this. This is the resistor. Okay, simultaneously you will measure all that. Okay, now just we measure the resistance. This is the voltage across the resistance, and this is the input voltage. And if we measure the input voltage as well as the resistance, the graph is like this. So if we calculate the resonant frequency, the resonant frequency like 1.6 kilohertz for the particular case of combination. So if I just write here 1.6 kilohertz, 1.6 kilohertz, then simulate it, then you see that the phase between the input and the output voltage is the same phase difference. Because if we just the phase difference is the same. So if you want to measure it, so 1 and 1, then for the input voltage and for the output voltage approximately the same. The change in not the peak of the voltage, the phase will be the same. So if we want to measure measure the current with respect to the voltage, like the time is very small, which is so. So now, if we want to actually simulate the circuit, so we have to go to the simulation, then analysis setup, then AC. So 1 hertz to actually resonant frequency is 1.6 or 4 kilohertz. So right, 4,000 hertz. 4,000 hertz, and the test point will be 20, like this. So if we just go to the AC analysis at the point this, we get the resonant curve. So if we want to change the scaling, like not linear but in logarithmic scale, we'll get the logarithmic scale. So this is actually 100 hertz to 10 kilohertz. So if we just change it, simulation, analysis setup, change it 100 hertz to 10 kilohertz, 100 hertz to 10 kilohertz, then the analysis is like this. This is the resonant curve. And if we change this and the data points much and more, if we just take the more data points, then we just take 100 data points. Then we just AC analysis, the curve will be smooth and like. So if we want to denote the point on the screen, so we have to go to the reference, then these points, the points is visible here. and if we want to change actually the phase, so we go to scaling, then linear scale, go to the phase in degree. So this is the phase difference, the phase curve. This is the phase curve at the 0 degree. Actually, the frequency will be 1.6 something. This is the resonant frequency. So if we want to measure the frequency at the 0 degree, so like actually at the 0 degree, it will actually 1.58 or 59 like that. So this is actually the resonant frequency of LCM, series resonance circuit. So we get the resonant curve. So if you want to realize both the curves in the same screen, then we have to go to right click and scaling, not scaling, is secondary. So if you want to measure the secondary and secondary in magnitude, then this the resonant curve and the curve for the phase difference in the same curve, in the same screen, and you can easily analyze the circuit and find the values of resonant frequency and the phase difference at which the current or voltage is can be done. Okay. So next, just
Sir?
okay.
Sir, there is a question. Is there any way to choose a dielectric material within the capacitor?
Dielectric, no. There is no question of changing the material within the capacitor. In this standard version. Okay.
Oh, okay, sir.
Is there any question?
No, sir. Till now there is no.
Here actually so many components are there. We can use the components only. Okay. And we can vary the values of this, but for the capacitor, we can actually, for the capacitor, so many capacitors are there. Capacitors, these capacitors, polar capacitor, semi-capacitor, variable capacitor, like that. So there is no question of changing the dielectric material within the conduction. Okay.
Okay, sir.
So now, if we consider it, want to realize the low pass and high pass filter in open, then low pass, high pass, so this is high pass. This is the high pass filter. This is the high pass filter. Simple circuit, the high pass filter circuit. So if we want to analyze the circuit or the simulate the circuit, so here we simulate the circuit like this. This is actually the linear. This is actually the transient response, and there will be certain phase difference of the transient response. And if we want to analyze the AC analysis, this is the low pass AC analysis. Okay. So if we just like this, if we want to change the scale, logarithmic scale, this is the AC response curve for high pass filter. That is the low frequency is blocked. That is the amplitude at low frequency is less than the high frequency. At the high frequency, the amplitude is greater. So the high frequency is passed through the circuit. So this is actually the characteristics or the curve for the high pass filter. So if you want to I want to show the different points at what point it will as a we just calculate the values of the frequency at which the amplitude is 1/√2 of the maximum amplitude. So if we want to calculate this thing, then we go here and we can the maximum amplitude, we can measure the maximum amplitude and then go to the 1 by root 2 and we get the half power frequency of the circuit. Okay. So now similarly, you can also for low power, for low pass filter, is open. Yes, this is the low pass filter. The circuit is this. This is the low pass, and if we want to change the scaling in logarithmic scale, then the curve is like this. So curve is more smooth if we change the step point. We increase the step point, then it will like this. Okay, so this is the characteristic of the low pass filter. So now, if we consider the case of the wind bridge oscillator, so wind bridge oscillator. This is the circuit diagram of the simple circuit diagram of the wind bridge oscillator, and I just construct this oscillator with the frequency of 1.27 kilohertz. Is the 1 by 2 pi hertz. So at the operating point, so we want to measure the DC analysis. So the wind bridge oscillator. This is the frequency response of the wind bridge oscillator. So we change the scale like logarithmic scale is like. Okay. So now, if we actually want to measure the voltage, oscillating voltage, not AC analysis, the transient. This is the output and the input. So this is the input and the output. So we just 1 and 2, 1 for 1, or 1 for the input voltage. And we also have 2 for the output voltage. So this is actually same phase. 1.1 is the same phase. 1 kilohertz frequency. Same phase. So this is the frequency response. Not this is the actually transient response, but frequency response. Yeah. If we change the scaling by linear, so we get the response. This is actually phase, not response. This is actually frequency versus phase. So if we want to reference scaling, go to not phase, the amplitude, so the magnitude, then this is the path, like this. Okay, this path. So now we go to Fourier, the circuit analysis, Fourier. The Fourier analysis, open analog Fourier. So we apply here. Actually, this is the as we change the view scale aspect ratio 200 for the half sine wave. This is the half sine wave because if we just analyze the circuit and it's not transient analysis, so we get the half sine wave. And here is the sinusoidal wave. So actually we design this circuit where the resonant frequency is 500 Hz. So 1 by third of the 500 Hz will be 167. So for 167 Hz, within the one half wave, we get actually 3 sinusoidals. So if we just see this, the 3 sinusoidals are there, 1, 2, and 3. So 3 full complete cycles are there. So if we change it by 250, that is by 2 for the half sine wave, by 250. This is only 2. 1, the complete half cycle. Okay. And what will be the phase response? So now, if we just and connect to the connecting wire, not here, this resistance is not equal. This, if you simulate it, see actually here for here 500 for 500. So we have to average this circuit. Sorry, average the amplitude, and if we just here input, this is the output. So no input is not required. So this is only we require a output voltage. This is the sinusoidal wave. Okay, the resonance. So if we just change this value, any change, 400. 400 is not in the actual sine wave. Because, but if we here 167 is 1/3 of the 500, that is 167 like this. Then we see sinusoidal wave, approximately the sinusoidal 167 like this. No, this is not the 167. 1/3. One. So if we just see, this is not the 1/3 because this is not the square wave and the half sine and the any other triangular and the square wave. But this is the this is actually for the resonance curve. For the resonance curve, you can just simulate the circuit for the resonance curve, AC simulation. This is the resonance curve. What 67 is the resonance frequency, 500 is the resonance frequency. So if we measure this is actually the 500. 500 Hz is the resonance frequency. With the help of the curve, the 500 is the resonance frequency. Okay. So now go to,
Sir,
okay.
sir, some questions have come up.
Hmm.
So, is there any way to calculate the percentage error?
No. No way to
And
calculate the percentage.
okay, okay. And the devices used here, are they ideal devices?
Ideal devices means there is no resistance within the inductor. No, these are ideal devices.
Okay.
These are ideal.
Okay. And does it have the option to connect to an external physical circuit for simulation?
From the outside?
Yes, yes, sir.
No.
I think so from the question.
No.
Oh, it's not possible. Okay.
Not possible.
And okay, sir. Until now, there's no other question.
So now we just go to the electronic circuit. This is all about the electrical. Go to the electronic circuit like diode, Zener diode, reverse characteristic curve, like that. So go to the Zener diode. This is the Zener diode. the simple generator circuit. So if we want to measure the voltage at the outside across the Zener, we use actually 10-volt Zener. So for the use of the Zener, we have to select the Zener by double clicking with the on the Zener. We use the Zener like this, 10 milliampere and 10-volt Zener. So select. We have to select it. If we unable to select it, then the performance will not occur perfect. Okay, so some error will be there. So now, if we just measure the voltage, so if this actually 20 volt, apply 20 volt, then run, then we get actually 10 volt because it's a 10 volt, 10 volt channel. So if we want to measure the current, so go to here and measure the different current for the different values of the resistance here. So now, if you want to simulate the circuit for different voltages, for the different input voltages, so we have to go to the simulation, then DC switch. Go to DC switch. This is the load regression. The 10 volt, this will constant. This is the load regression. Okay. So now, for the line regulation curve, we have to measure the current. So here, the line regulation. Okay. So here now for key characteristics. File, open, CDC. So this is the circuit diagram of a simple DC common emitter configuration. So here actually two sources are there. One is V1 and another is V2. So if we want to draw the circuit, draw the curve or draw the output characteristics curve, that is for the variation of VCC, and we show the variation of IC, then we have to do some changes. The DC. Here DC, in the DC enabled two sources, one is V1 and another is V2. So if we want to vary or want to draw the output characteristics curve, V2 is the dependent variable. V2 is the independent variable because due to the variation of V2 or the VCC, we can measure the IC, and for a fixed value of IB. IB means V1 is constant. So here we just write V0, V1 is the secondary, then 0, then 10, then 2. 2, if we just write here, not 2, then 5. 5 means actually step value. Step value 5 means we do actually two for two different IBs. For two different IBs, we measure the various values of VCC and corresponding IC. So here is 0, V2 is the VCC, 0 to 10, and then 10 100 for 100 step, for 100 step. Step value is how much? Step value is 0.1 volt. So 0.1. 0.1. No, step value is 1. So run analysis. Then the voltage. Micro DC switch. We have to change the DC switch. Sorry. Simulation analysis setup. DC switch. 0 to 10. Step value 1. 0 to 10. Step value 5. Only 0 to 10 for the why it is in microsecond. Oh, sorry, DC sweep. Very sorry, very sorry. This is actually transient response. This is the DC sweep. DC sweep. This is the output characteristic curve. This is the output characteristic. Okay. So if you want to draw the input characteristic, we have to slight change. Like this here, this is actually V1 and this is V2. So here the V1 is from 0 to 10 and this is 0 to 1 and this is also 1. This is actually 10, this is 5. This is sweep, this is the input characteristics. With the variation of actually keeping the voltage V2 is fixed. Keeping the voltage V2 is fixed, the VC fixed, you can change the value of IB and VB. This is VB and this is IB in microamp. For different values, so if we just put one value here, like simulation analysis setup, DC for one value, so 10 steps. V2 is changing from V2 is changing from for two values. So V2 for two values, not one. This is actually for 5 steps. 5 step is 5 means only 2 values, and this is from V1. V1 is actually V1 changing of V1. V1 run analysis. Simulation analysis. V1 is 5. Variation of V1 is greater actually. This is V2 only 5 steps and V1 is 1. For the variation of input voltage. This is the output input characteristic. This is the input for different values. Okay. So now go to the C amplifier. C amplifier. Open C amplifier. Any circuit. C amplifier. This is the C amplifier circuit. If we run it, then this is the response. This is actually the response curve and this is the phase curve. So 180-degree phase. So phase difference between input and output 180, so 175 degrees, so like 180. So this is the response curve, frequency response curve, and this is the phase curve. The frequency versus phase and frequency versus voltage.
Sir, sir, another question will come up related to the C amplifier. So it's saying that if we make a CE amplifier circuit and connect and disconnect the emitter capacitor, will we be able to see the effect of the capacitor on the amplified signal?
Yes, yes, it will be possible, because if we just disconnect the capacitor 26.63 microfarad capacitor, disconnect this, then the effect of must be there on the amplification of the amplifier.
Okay, sir.
Must be shown in the circuit, must be shown in the graph also. Okay.
Okay, sir.
Any other question?
No, sir. No, sir. There is
So
no other
now
question.
we go to the operation amplifier. So open op-amp integrator, or op-amp integrator is same thing like the integrator means the low pass and differential means high pass. So these are same. So I am just going to the op-amp 741 IC op-amp integrator differentiator adder, op-amp adder or subtractor like this. Adder, op-amp adder. So this is the op-amp adder circuit. So if we want to change the values of these two values, so this is 4.9 the 5 volt, because gain is the 10, the 1k, so 0.3 plus 0.2, so 0.5 into 10, so 5 volt. So we just change the voltage by 1.4 volt, then simulate it, and we get is the 6 volt. So 0.4 plus 1.2 is 0.6 volt. If we change this voltage, you can also change the voltage of the output. Now, if we want to draw the curve of the variation of the input voltage with the output, then we just go to calculation, analysis setup, DC. So DC actually variation of V3. What is V3 actually? Actually, what is V3? V3 actually 0.4. This voltage V3. So V3. So variation of V3 from 0 to 0.5. That is 500 millivolt. That is 0 to 0.5. And by the step of 0.1. Okay. Then run analysis. Then go to the DC switch. The curve. This is the curve, because the point input is 0.5 millivolt. Sorry, 70 millivolt and minus 2.7, and you can change the voltage accordingly. You can output voltage will change. This is the curve. Okay, for the adder circuit. Okay, you can also measure with the help of the DC voltmeter also. Okay. So now we also, in the same way, you can construct the differential. That is the voltage difference between the two voltages. You can see all the things. So now, of integrator, differentiator. Now we can also implement the actual ladder, square wave generator. So many circuits are there. So open. So actual ladder. Circuit. So this is the actual ladder circuit. Okay. So just here is 0, 0, 0, 0. If we just put 0, 0, 0, 0, 0, 0, 0, 0, then we simulate it, then we get minus 4 volt. Sorry, 0, 0, 0, 0. Also 0, 0, 0 volt and 0 volt. 0, 0, 0, 0. We get actually 0 volt. Theta 325.5 microvolt means 0 volt. So 0, 0, 0, 0. So 0, 1, 0, 0, 1. 1, 0, 0, 0. 1, 0, 0, 0. This is actually 0.333 millivolt. That is 0.33 volt. This is actually how it is coming. Actually, for 1111, you will get 5 volt. We design the circuit such a way that the 111 and 1111, and if we simulate it, we get a 5 volt. -5 because this is the inverting amplifier, and 000 volt means 0 volt. In between, if we change the voltage 0001, 0010, 00101 like that, if we change the voltage, then we get actually 15 steps, the 16 steps from 0 to 15. 1111 is 15. So for 1111, we'll get 5 volt. For 000 volt, 000 case, we get 0 volt. So 0001, we get 1 by 15. Actually 1 by 15 volt. Then 0010, we get 2 by 15. 0011, we get 3 by 15, like that. Then 1111, we get 5 by 15 by 15. So we'll get 1 volt. Okay. So here is actually 1 by 15 into 5, 2 by 15 into 5, 3 by 15 into 5, because 5 volt is the reference voltage. So we can measure the different voltages. So if we just 1, 1, 1, 0, so we'll get minus 2.33 volt. One, 0, 1. We get, if we get minus 3.66 volt, the minus 3.66 volt actually 14 by 15 into 5, like that. Okay, so this is the actual ladder, and we also implement a square wave generator with the help of the op-amp. Square wave op-amp, square wave generator is simple. This is the square wave. This is the square wave generator, and if we just, this is the square wave. And here the voltage is 150 volt, and here the 5.1 volt. Because of 5 point, approximately we get a 5.6 volt channel. Ratio V, the scale behind there, then simulate it. This is the square wave. So many circuits can be implemented with the help of the circuit maker software, and you can analyze it as well. Okay, thank you. So this is all about the circuit maker. So many circuits I will construct, but due to the shortage of time, some circuit just I have implemented earlier, then I show you. Okay, thank you.
Thank you so much, Shubhendu sir, for this wonderful presentation. And
If there are any more questions, we
Is any more questions from the audience?
no, sir, no questions have come up right now.
Okay, thank you.
thank you, Shubhendu, for this wonderful presentation and demonstration. I think the students must have found it very interesting, and they can try it at home and practice for themselves before actually doing the experiments in the lab. Thank you. And
Thank you, Gayatri. Thank you.
Now we will start with our third session. I think now Dr. Niladri Banerjee has joined.
Yes, I'm around. Yeah.
Yes. Dr. Niladri Banerjee will Dr. Niladri Banerjee he'll give us a presentation on micromagnetism and object-oriented micromagnetic framework. Today will be the first part of his presentation, and he is going to talk to us tomorrow also. I'll just give you a brief introduction to his to Dr. Niladri Banerjee. He is a senior lecturer, associate professor in the Department of Physics at Loughborough University in UK. He leads an experimental group of several PhD students and postdocs focusing on studying the interaction between magnetism, superconductivity, and spin-orbit coupling. He did his undergraduation in material engineering from Bengal Engineering College, Shibpur, and his MTech from IIT Kanpur. In 2008, he received the Dr. Manmohan Singh Scholarship to study PhD in Material Sciences from University of Cambridge. From 2011 to 2015, he was a postdoctoral fellow at Cambridge and a junior research fellow at Wolfson College, Cambridge. Now I'll invite Dr. Niladri Banerjee to kindly give us his presentation.
Thank you very much. I'd like to thank the organizers also for inviting me to give this talk. This is my first time in Google Meet, so I'm sure there will be some problems to resolve. I'll see. Okay. Can you see the presentation?
Yes, we can see.
Okay, right. If there is any problem and if you cannot see or if there is any question, I'm happy to take. So just feel free to interrupt me in the middle. Okay, so, right. I'm guessing that this is a sort of a mixture of faculties and students. So I will keep the things simple because for it to be accessible to the students. And the first question is, that why do we want to study micromagnetism and what is micromagnetism? And what I'll do in this talk, I have kept it more or less flexible. So I'll try and explain in the first few slides that why do we need to study micromagnetism? And then if possible today, I'll introduce the software. And in tomorrow's session, we will see a few simulations from the software. If possible, we'll try to do some simulations today also. So right, so we are starting with some very basics of ferromagnetism. And for the undergraduates, for who are in first and second year, just to mention that what you understand by a magnet, here I'll be mentioning it as a ferromagnet because to exclude other types of magnetism like diamagnetism, paramagnetism, or antiferromagnetism. So whenever I talk of ferromagnetism, it is the usual sense of magnets that you understand. So as you can see, I have now replaced ferromagnetism with magnetism now. So I will interchange and use it throughout the presentation. So next question is that why magnetism at the nanoscale is important. So this is what we will try to understand, that why do we need to understand the nanoscale magnetism. And then we will go to some elements of micromagnetism. And finally, we'll introduce a software, Object-Oriented Micromagnetic Framework, or OOMMF. Now, the question is that why OOMMF? I mean, why suddenly am I doing a presentation in OOMMF? So we were having a discussion on how to manage lab sessions during the lockdown, or if there are future lockdowns, if lab access is restricted, how do we manage the lab? So we had to find some resources, as you have seen in the first two presentations, that whatever experiments or quote-unquote experiments we can do online. So this is not exactly an experiment, so to say, but this is a program that will integrate what people are being taught, or what students are being taught in nanotechnology, for example. There is a lot of modules I hear nowadays in BSc level and MSc level on nanotechnology or nanomaterials. Now, I have slight reservations with the term nanotechnology or nanomaterials because it's a very vast field. I mean, there are many different things. So primarily what I have learned is that in India, the focus is mainly on optical, magnetic, and electronic properties of nanomaterials. In some engineering departments, you also study structural properties of nanomaterials. So here, since in physics, people often study electronic, magnetic, and optical properties of nanomaterial, we are going to focus on magnetic properties of nanomaterials or thin films. So this is why magnetism at nanoscale we are going to study in this presentation. And what you will find is that because of reducing the dimensions to the nanoscale, there is a very drastic change in the electronic, magnetic, and optical properties. Now, many of the effects are often related to quantum mechanics, why this happens, why the properties change, why the band structure changes, why a material, when you make nanopowders, why it has a different color or it has a different electronic property. It is same for magnetism as well. When you reduce the size of a magnet, it has very different properties. Now, what do I mean by different properties? It can have, for example, very different strength of the magnetism. It can behave completely differently when rotating under an external field. So there can be various aspects which change because of this going to the nano dimension. So first, in these few slides, in the first few slides, we are going to discuss at what changes and what change are we focusing on. Interestingly, whatever change we will be discussing in these couple of lectures will not be related to quantum mechanics at all. It is a very simple classical magnetism argument. So there is nothing sort of fancy quantum mechanics involved here. So and we will show that even in going from the classical magnetism, how much variation you can get in the properties of a magnet when you go to the nanoscale. So let's start with the very sort of simple ideas, is that if you have a magnetic material, as you might remember from, the students might remember from their high school days or from their BSc, that if you apply a magnetic field and you plot the magnetism versus the applied field, the ferromagnetic material, the response of the magnetic material is what is known as a hysteresis loop. So it traces out a loop like this. So you start at a high field. So for example, let's put a number here. Let's say you start at 200 millitesla. Tesla is a unit of magnetic field. So you start at 200 millitesla when the magnetic material is saturated. At the moment, we are not concerned about whether it's a nanomaterial, whether it's a thin film, whether it's a bulk magnet. Forget about all complications. Just think that it's a bar magnet that you have purchased from the shop. So you apply a field of 200 millitesla using a solenoid, for example, and passing a current. So all the magnetic moments, or the tiny little magnets, the tiny little domains that form the magnetism, everything is saturated here. This line is exactly not parallel to the h-axis, and the reason it may not be exactly saturated, or it might be nearly saturated, so that's why I haven't made it parallel. So most of it is saturated at point 1. You start reducing the magnetic field, you trace out this loop. How do you trace out this loop? The equipment that you are measuring the magnetization, it is recording the value of the magnetic moment. There are different ways to measure magnetization. For example, you can use what is known as a vibrating sample magnetometer. So you put the sample in the VSM, or the vibrating sample magnetometer, you measure the magnetic response as you change the externally applied field. So you start at a high field, you measure a large magnetization value. You start reducing the field, I'm moving over the red curve, and you hit a point 2, for example, and you notice the magnetic value of 2 at point 2, the magnetism at point 2 is less than the magnetism at point 1. So something has changed. So some of the magnets, some of the domains have rotated on the other side. You increase the field a little bit, and what you will see is that the magnet, suddenly the magnetism flips the direction and it goes to the other side. so to the negative side. And again, as you start increasing the value of the magnetic field from high negative field to positive field, you will trace out this curve, and at this point it suddenly flips to the positive direction. Now, why this is hysteretic? What do we mean by a hysteretic response? The meaning of hysteretic response, I mean, magnetic materials are not the only one which shows hysteresis. There are many materials, like, for example, elasticity, for example, if you plot the stress versus strain, it also shows a hysteretic response. So what do we mean by hysteresis? So, for example, if I tell you, what is a magnetic moment at a field value of, say, plus 10 millitesla when we are here? Now, if it were a straight line, what you would do, you'd drop a perpendicular and you say, oh, that's the value of magnetism here. But now you see there is a problem. If I ask you what is the value of the magnetic moment here, you have two options. Either you go here or you can come down here. So you don't know exactly what is the exact value of magnetism. For that, you need to know the history of the sample, which means whether the sample is going from positive to negative field. In that case, the value of this field will be positive m, or if it is going from a negative field to a positive field, in that case, the value at this field plus 10 millitesla will be negative m. So this is what is meant by hysteresis, that it remembers. So it depends on the previous history. Here are some basic definitions which you already know from your high school, that if you apply this magnetic field B is related to the magnetic field H by this relation. This is a mu naught is the permeability of free space, and this relation is true if it is in vacuum. But if you have a magnetic material, then B is equal to mu naught times H plus M, where M is the magnetic moment per unit volume of the sample. And some examples of magnetic materials are iron, cobalt, nickel. These are elemental ferromagnets at room temperature. By elemental ferromagnets, I mean that they are not alloys or not compounds. There are other elemental ferromagnets. They are magnets at low temperature. For example, all the rare earth magnets, holmium, dysprosium, samarium, but we are not bothered about those here. Let's just focus on iron, cobalt, and nickel for the moment, the ones that we are familiar with. So now we know that how to plot the hysteresis loop. So if you put your sample in a vibrating sample magnetometer, this is a loop that you can get. Now, in order to get a more pictorial description of what is happening, let us look at the energetics. What is going on in the energy landscape? So this is a picture that you had from, for example, all the students would have seen this picture in their high school or in their BSc textbooks, that at point 1, all the tiny little magnetic moments are aligned in the same direction because you applied a magnetic field, external field, which is pointing from left to right. So all the tiny moments have aligned themselves. For now, you can think that these tiny moments are simply like compass needles, nothing more than that. If we plot the total energy as a function of the field, what we will see that it has two distinct minimas here. And if I represent the state of the material by this red blob here, it is staying in this minima. So it is staying in plus m. So this is plus m. As you start increasing the field in the opposite direction, that is in the negative h, in this direction, as you start increasing the field, what will happen to this energy is that this barrier, that is for the particle to go from plus m to minus m, it has to overcome this barrier. So to go from plus m here to minus m here, it has to overcome an energy barrier. Now, if you apply a field in the opposite direction, in the negative direction, this barrier will start to reduce. So it will be a smaller barrier now. And what will happen to the picture? What will happen to the magnetic moments? You'll see that some of the moments will start turning at the corners, turning in the opposite direction. So why is it turning in the opposite direction? Because here the compass needles are following the external field, which is trying to force them in the other direction, in this direction. If you increase the field a bit more, so if you increase the field from this position 2 to position 3, you will see that this minima now becomes a saddle point, which means the ball here is no longer stable, and it will roll downhill and settle at the lower minima, which is minus m. So it settles down here. So this behavior of the magnetism can be thought of as a ball in a hill with two valleys. So it is in one valley with plus m, you apply a field, it reduces the barrier gets reduced. At one point, the ball is no longer stable here, and it simply rolls down to minus m. And pictorially, what happens? All the little compass needles now point in the opposite direction. By compass needle, I don't mean that there are physical compass needles. I mean tiny little magnetic domains. They point in the opposite direction. Now, that's the simplest possible picture. Why have I mentioned this picture? Because for two reasons. One is this is what we think is going on. This is what is ingrained in our minds, that whenever I apply a magnetic field, the magnetic moments will point in the same direction, will align itself with the field. Whenever I reduce the value of the field, it will start to misalign and then flip over to the other side. So this is what we have in mind. And towards the end of the talk, hopefully by the end of today, we will see why this picture is not true in thin films on nanoparticles. What changes? And the second reason I introduce this picture is for this energy landscape. Why is this energy landscape important? Because in order to determine what happens to the magnetization, you can simply write down the total value of the energy and do a first derivative, equate it to 0 to find the equilibrium point. And this is what OOMMF actually does. So before going into the details of OOMMF, let us look at what are the interactions that are important, that are relevant in magnetism. So let me go back one step. So what we know from high school physics is this is the North Pole, this is the South Pole. So this has a free North Pole and this has a free South Pole. And North and South attracts. So which means that if there are two magnets, the North Pole will align with the South Pole of the other magnet if you have a magnet on top. So this is known as a dipolar interaction. So let's go to the dipolar interactions. So if this is the magnetic moment of one magnet, so this is one compass needle, interacting with a second compass needle, they will align anti-parallel because of dipolar interactions. And you can write down the energy of the dipolar interactions with this functional form. And this mu1 is the magnetic moment of the first magnet, mu2 is the one of the second magnet. And the question is that, okay, fine, I understand that North and South attracts. But what happens here? What happens if you look between the two domains? What happens if you're looking at this arrow and this arrow? Here, North and South are not attracting. They're aligning parallel. But you will say that, okay, fine, they're aligning parallel because there is an external field. Fine, if you remove the external field, you will still see that the arrows are aligned. So what is keeping the arrows aligned? What is the interaction between the arrows? Can dipolar interaction explain that why the arrows are parallel? Let's go back to the dipolar interaction. So this is the energy of a dipolar interaction. Let us put some values. For example, let's assume that these are unit magnets, so one Bohr magneton. For undergraduate students, you can go back and read what is a Bohr magneton. So this is one Bohr magneton, and let's assume that the distance between the two magnets is 1 angstrom. You will get an energy which, if you convert it to a temperature scale by kBT, so E equal to kBT, and you find what is equivalent temperature, you will find that the equivalent temperature is 1 Kelvin, which means that if you only consider the dipolar interactions, it can align with a strength equivalent to 1 Kelvin. So if the temperature of the sample is more than 1 Kelvin, if it goes to 2 Kelvin, the thermal disruptions, the thermal motion will overcome the dipolar interaction. So it's a very weak interaction. It's in fact the weakest interaction possible. So clearly, if I go back one more slide, iron, cobalt, and nickel, if you remember from your high school that they had very high Curie temperature, the temperature at which a ferromagnet becomes a paramagnet. The temperatures are often of the order of 700, 800, or 1000 Kelvin. So how do you explain the alignment in iron, cobalt, and nickel based on dipolar interactions? Because in dipolar interactions, the Curie temperature is 1 Kelvin. It's very weak. So for that, you need something else. And that is responsible for magnetism. So this is the part where quantum mechanics comes in. But I have assured you that we are not going to do much of quantum mechanics now. So this is the only part that I will be talking about quantum mechanics here. And the reason I'm talking about quantum mechanics, it will become clear when we do OOMMF. So it is known as the exchange interaction. So exchange interaction can be explained quantum mechanically, and it is an electrostatic interaction which it respects the Pauli's exclusion principle and the Coulombic interaction. So simply stated, it tries to separate the electrons as far as possible so that it reduces the Coulombic repulsion. If you go through the basic quantum mechanics of exchange interaction, it is very simple. You can take any textbook in magnetism. I have recommended a textbook by Stephen Blundell. If you get access to that textbook, it's a very good textbook. It's a very sort of concise description of magnetism. So in exchange interaction, you'll see that if electron spins are represented by arrows here, remember the arrows here represented magnetic moments, compass needles. Here, imagine that these are electron spins, because magnetism ultimately arises from spins. This comes from quantum mechanics. So if these are electron spins, what is going on in between them so that they are aligned parallel? I mean, they don't need to align parallel. They can be randomly oriented, but something is there to make them parallel, and that is the exchange interaction. So if you now write down the energy of the exchange interaction, I've written down the Hamiltonian of the exchange interaction. For undergraduate students who are not used to Hamiltonians, don't worry, this is simply an energy term. So this will be negative SI dot Sj. SI is the ith spin, say there's the first spin, Sj, the second spin. So the interaction between Ij can be represented as SI dot Sj with a constant Jij. Jij is a coupling constant between Si and Sj. Now you can see that if Jij is greater than 0, therefore Si and Sj has to be parallel, because Si dot Sj will give you a cos theta term, and cos 0 is 1, so that total energy will be negative because it has a minus sign here. However, if J is negative here, less than 0, then in order to keep the total energy negative, Si dot Sj has to be anti-parallel, because cos 180 degree is equal to minus 1. So that then gives you the minus sign in the beginning. Which means that if Jij, or the exchange interaction constant, is greater than 0, the spins will align parallel, which gives rise to ferromagnetism. If you put the values of the constant and if you put the values of the spins, you roughly get a temperature which is equivalent to 10 to the power 3 Kelvin, so 10,000 Kelvin. So this means that exchange interaction gives you significantly stronger magnetic interaction than it is possible with dipolar interaction. So Curie temperatures, high Curie temperatures in iron, cobalt, and nickel can be explained on the basis of exchange interactions. Now let me tell you one thing, that since this is a 2-hour session, I am skipping a lot of details. There are a lot more complications, obviously, in magnetism and in OOMMF, but I've tried to keep it as simple as possible so that the whole aim is to give you just the basics. The remaining part you can study yourself and you can develop your understanding. So, okay. So these are the two interactions that we now know, the dipolar interaction and the exchange interaction. Let us see, there are 2 more interactions. And all these
Niladri, there is a question. Do you want to take it now?
Yeah, sure.
Okay. Dr. Niharanjan Mishra, he's asking that does the isotopes of iron produce similar magnetic property at nanoscale? I am assuming it to be same as magnetism is an atomic property.
It's an interesting question, and it obviously resonates with what I was saying just a minute back, that there are many complications that I won't be able to go to. Firstly, this concept that magnetism is atomic, there is a bit of a problem in there, because this does not capture the atomic part of the, from this you can say that, well, magnetism is atomic, but there are reasons from which you can say that this is a nearest neighbor interaction, which shows that there are more than 2 spins involved. So magnetism actually comes from sort of a collection of atoms. So it's a very good question that when magnetism breaks down, like whether can you call a magnetic atom an atom magnetic or two atoms magnetic? So there are a lot of studies on this. So to answer your question, it is not as straightforward as I would think. So isotopes of iron, it would depend upon the band structure. What the band structure is, what is the densities of states at the Fermi level. And if you reduce it, reduce the dimensions, the densities of states at the Fermi level may not change as simply as in all isotopes of iron. So if you have a different crystal structure of iron, it may not be magnetic at all. It might be paramagnetic. So there are many more complications. So it is not very straightforward. You have to know the exact material. You have to go to the nanoscale. You have to see how the band structure changes in order to precisely answer that. So, okay, so coming back, I hope that answered the question. But if you have further questions, please feel free to put it down. Okay. Right, so now, sorry, is there any more questions?
No, you can carry on now.
Okay, thanks. Okay, so now we know that there is dipolar interaction, there is exchange interaction. So let's look at the next one, the Zeeman interaction. This is a familiar interaction. We all know that you apply a magnetic field, all the magnetic moments will align. What is the energy associated? It's minus m dot h, which means that the magnetic moment is going to align parallel with the magnetic field. Because if it aligns anti-parallel, m dot h will be negative and the energy will be positive. It has to align parallel to give it a lower energy, a minus sign. So this aligns all the magnetic moments with the external field. This we all know. So these are the three interactions we are familiar with. There is one more interaction, which is interesting, and it makes things a bit more complicated, especially in the nanoscale. This is the spin-orbit interaction. I'm not going into the details of what is spin-orbit interaction, but very simply, when an electron is moving around an atom, so the red dot is the electron, it is moving around an atom. Since it's moving around the nucleus, since it's moving around the nucleus, it can be thought of as a current loop. And it will create a magnetic field that will be pointing from the center of the plane outwards. And that magnetic field can interact with the spin of the electron, giving rise to what is known as the spin-orbit coupling. Now, at this point, we don't need to go into any more complications, but why spin-orbit interaction is important? Because imagine if you're considering iron or cobalt, for example, is forming a lattice. It can form a face-centered cubic lattice or a simple cubic lattice or a hexagonal close-packed lattice. So the cobalt atoms will be arranged in different arrangements in space. Now, which means that the electron distribution will not be isotropic. Because of this, what happens is the most important thing, is that even when you apply a magnetic field, the magnetic moment represented by the red arrow may not align with the field. So this picture, the Zeeman interaction picture, may not be true if there is spin-orbit interaction. Now, you can say that, well, I have read that spin-orbit interactions are very weak, and Zeeman interaction is very strong. So obviously Zeeman is going to win over spin-orbit. And you'll be absolutely right that Zeeman will win over spin-orbit. But under certain circumstances, you can enhance the spin-orbit interaction by going to the nanoscale, and there the Zeeman interaction might be, the spin-orbit interaction might be as strong as the Zeeman interaction. So now you can see a sort of coherent picture emerging out of all this. What is a coherent picture? So there are four energy terms. One is a dipolar interaction, the guy who tries to align everything anti-parallel, north-south interaction, north attracts south, south attracts north, but it's a very weak interaction. The second guy is the exchange interaction. It's a very strong interaction. It is in fact the strongest interaction, which tries to align everybody parallel. In presence of an external field, there is a Zeeman interaction, that the external field tries to align everything parallel. And in certain cases, there can be spin-orbit interactions where it tries to align along certain preferred crystallographic directions. So there are four energy terms competing with each other in a ferromagnetic material. And the equilibrium direction of the magnetic moment will depend upon the strength of all these competing interactions. So that's the summary of the whole story. And that's the reason I have gone into the details of all this, to tell you that These are the 4 interactions that are mainly the most important interactions. There could be some other interactions. I'm not going into details of that. But these 4 interactions play a part. They fight against each other to dictate the equilibrium direction of the magnetic moment when you apply an external field. So now, let us for 1 minute go back to this picture. Now you can see this picture may not be true because there are 4 competing interactions. This picture only takes into account 2 interactions, the Zeeman and the extend interaction. So you can have some deviations from this intuitive expected direction to some other directions depending on the strength of these interactions. And this is what OOMMF tries to solve, or solves in certain situations, but you can have further complications as well, So we'll see in a second. Now, before we go into OOMMF, let's quickly look at some applications of magnetism at the nanoscale. They can, again, this is a very broad topic. As I told you that nanomaterials is a very broad topic, it doesn't make sense to talk about a course in nanomaterials because it's extremely broad. You can just give an overview of nanomaterials. So here, as we discussed, we are talking about magnetism at the nanoscale. So even then, it can be very broad. It can be magnetism of nanoparticles, it can be magnetism of thin films. Here, we are going to talk about magnetism of thin films. And before going to OOMMF, I will just quickly show you one application of magnetism of thin films. So this starts with, whoever was born in the 70s and 80s will know, but people born after 2000 would not have heard about this. So back in our school days, we used to have floppy drives, which were like 1 megabyte or 2 megabyte of storage capacity. And then you take all your important Word document or your files in the floppy drive and you go through a magnetic scanner and you lose everything. So this was very common in our childhood. But notice that something changed around the 1990s. And this is the plot of the areal density, that is a megabyte per square inch of the hard drive as a function of the year. So around 1990, the curve starts to go up. And if you look from 1960s, it is 10 to the power minus 3 megabyte per inch square. So you can imagine that 1 inch would be recording 1 kilobyte. So to have 1 megabyte, you will need the size of a room, a big room. Your bedroom will be equivalent to the size of 1 megabyte memory back in the 1960s. Now, in 2010-ish, it has gone to 10 to the power 6 megabyte per inch square. Now it is of the order of terabyte per inch square. So this is 9 orders of magnitude in 40 to 50 years. It's a fantastic increase. So this is 17 million times increase just from here to here. So what drove this growth of hard drive capacity? So something happened here. As you can see that it is the introduction of the first magnetoresistive head. What do we mean by head? It is a sensor that reads the information from your hard drive. That started using something known as magnetoresistance. I'll explain in a second what magnetoresistance is. And here, IBM started using giant magnetoresistance. So I'll actually first explain what giant magnetoresistance is. And this is where magnetic thin film is important. As you see that the first thin film head has been introduced. Because magnetic hard drives are made of magnetic materials, you need to read information from the hard drive, so you have to have a magnetic sensor. So that is where thin film comes in. So now, let's look at a ferromagnet. So going back to the magnet again. All the tiny little red arrows that you saw, now I have replaced by electrons, the green arrows, the blob with the green. So these are upspin electrons, these are downspin electrons. This is iron, for example. And you can see that the number of green balls is greater than the number of red balls, which means that it has a net magnetic moment in the upward direction. This one, the green arrow. This also means that if you inject a current of electrons, this I gave in my first talk, so whoever attended the first talk would find some similarities with the next few slides. So if you inject a charge current which has equal number of up and down spin electrons into the ferromagnet, what will come out is a spin polarized current. It will have excess number of upspin electrons. So if you go to the band picture of the ferromagnet, I think in undergraduate you learn a little bit of the band structure of materials. If you go to the band structure of a ferromagnet where you plot the energy as a function of densities of states, what do I mean by densities of states? It's simply the rooms available for the electrons to travel. Where do the electrons travel? They travel here. What is this line? This is the Fermi energy. All the states below the Fermi energy is filled up. The electrons cannot go there because electrons are fermions. They cannot go to occupied states. They have to go through free states. So they go through here, all the rooms that are available. So this is simply in a building. All the rooms that are empty, you can travel through. All the rooms that are filled up by other persons, you cannot enter, like in a hotel. So you inject a spin zero charge current, you see that there are excess number of there are fewer number of downspin electrons compared to upspin electrons. The rooms are more. So what you get out is more upspin electrons. So it has polarized the charge current. Okay, that's fine, that's good. What do we get out of it? It has polarized the current. So if I now look at a normal metal, copper, it has equal number of densities of states for the downspin and upspin, which means you inject initially spin zero charge current, you get out a spin zero charge current. So now if you combine this ferromagnet and the non-magnet, what you get is what is known as a spin gulf. Now what is a spin gulf? So you have a magnetic material, cobalt for example. Imagine that the thickness of the cobalt is 10 nanometers. This
Neeraj sir, you are not audible.
Niladji, please unmute yourself.
Unmute,
Someone has muted yourself by mistake. Yeah. Niladji, please unmute yourself.
sorry, can you hear me now?
Yes, yes.
Yeah.
Oh, sorry. Okay, I didn't notice. I heard a noise, but I thought, okay, right. Sorry. Till how much did you hear? Did you hear this spin
Spin
gulf?
back. Spin
Yeah,
back.
this
Okay.
spin back. Okay.
Okay. I'll go back. Sorry for that. So so here what you see is that this is one ferromagnet, say cobalt, and a copper layer, and another cobalt layer, for example. Why do we have the copper layer? To separate the two ferromagnets, so that they don't behave as a single magnet. Now, the first ferromagnet, you inject a charge current, it spin polarizes. So all the polarized electrons travel through copper and they encounter the second magnet. The second magnet is also pointing in the same direction, so it has excess upspin electrons can pass. Now, if the second ferromagnet is pointing in the other direction, what happens is the first ferromagnet will spin polarize all the electrons. Those spin polarized electrons, the up arrows, they pass through copper nicely. When they encounter the second ferromagnet is pointing in the wrong direction. So these electrons cannot easily go into the second ferromagnet, they will be scattered. So it will result in a high resistance state compared to this state where it is low resistance. So this device can control the resistance just by turning the magnetic moments. Now, I'll go back to the laser pointer, sorry. Yeah, this device can control this resistance by just turning the magnetic moments. Now, why this is fascinating? This is fascinating because this is the first device that you have seen as undergraduates, or possibly postgraduates even, that can see the spins of the electron. Because notice when I discuss about the change in resistance, in that discussion, I did not bring out the charge of the electron. I discuss about the spin of the electron. And now this is the first device that you are seeing that is sensitive to the spins of the electrons. Now, why it is good to be, why do we make so much of noise about that? Well, you can see the spins of the electron. Because spins can flow without getting scattered. So you can, if you have a spin current, that is far less dissipative than a charge current, which means less heating. So anybody using a laptop knows that, or a phone knows that it heats up when you charge or when you use it because of Joule heating. So if your phone or your laptop completely works on spin currents, the heating will be almost zero. It will be very low. So you can build up more powerful computers. So this is a birth of something known as a spintronics. It was in the 1980s. And this, IBM used this device as a head, as a read head, to read information from the hard drive. And for this, Albert...
there is another question that how much resistance will be there generally in a memory device?
Okay, so if you are talking about these spin valves, if they are fully metallic spin valves, you are looking at resistances of the order of few ohms, or even fraction of an ohm. And the change in resistance is often of the order of tens of milliohms. It's very low, but still it's quite large for practical purposes. If instead of copper, you have an insulator here, say for example, aluminum oxide or magnesium oxide, then the resistance could be of the order of kilo ohms, and the change in resistance could be of the order of few percent of kilo ohms. So we are talking about hundreds of ohms of change. So the hard drive read head that you have in your laptop now has an insulator. It doesn't have copper. So it's of the order of hundreds of ohms or kilo ohms. So,
okay, thank you.
So because of this, I'll just take one more minute to say something important. I mean, the reason I have put arrows, it seems that it's a trivial achievement, that you have put a ferromagnet, okay, it spin polarizes electrons. If you have a second ferromagnet that detects electrons, it's simple. But imagine, just think for a second, spin is not an arrow. Spin is a quantum mechanical property. So you cannot see a spin. So it's a completely quantum mechanical property of an electron that is very difficult to detect in that sense. So to think of technology, to think of something which depends on the property of electron that is purely quantum mechanical, to exploit that property is something fantastic. And that's the reason that Albert Wirth and Peter Grunberg was awarded the 2007 Nobel Prize in Physics for spintronics. And this has completely revolutionized two things. One is this hard drive. Now it has far higher areal densities because your sensor, the sensor that it uses, it can be very small. So you can pack more information per square inch. Now, this is the beginning of OOMMF. So I've discussed for the last 30-40 minutes of a background. But now we start to appreciate that why we need OOMMF and why or how it can connect to some of the courses that you're doing in your undergraduate or postgraduate. The size of the devices. The size of the thickness of the layers are of the order of nanometers. And the X and Y dimensions are often of the order of hundreds of nanometers, like 50 to 100 nanometers or 200 nanometers. Now, if this is a fantastically small device, it's a tiny device. So now the question is, this arrow that I have drawn, this large arrow, which is a magnetic moment, all the magnetic moments are pointing in the same direction. Will this picture hold true anymore? You have seen that there are four energies that are competing now: the dipolar, the exchange, the Zeeman, and the spin-orbit interaction. And when the size reduces, dipolar interaction may not be very weak anymore. And we will see that how dipolar can become strong. Okay, so that's why we need to understand that what is the magnetic state in these magnetic materials. Why? Because imagine this is not an arrow. This is some horrible curly structure. So the change in resistance that you will get will not be as large as if you have a uniform magnetization. So you need to know what are the interactions that are competing in order to give it a uniform magnetization, or sometimes you may not even want an uniform magnetization, you want a non-uniform magnetization. So how do you go about and think, how do you design your device in order to get a non-uniform magnetization? For that, you need to see the magnetization. But it's very difficult to see a magnetization at these small scales. So OOMMF is a very useful tool which can simulate and give you what it looks like, the magnetization. This is an example of an image that was taken of cobalt nanoparticles. And you will see that this is an atomic force microscopy image. These are individual cobalt nanoparticles. And they did a measurement where they could see the contrast between the domains. So darker regions are pointing in this direction, and the fainter regions are pointing in the opposite direction. So you see that within one particle, it has broken into two domains, one in this direction, one in this direction. But this image is not really clear. I mean, to go from here to here, it's not that simple. And this is not a straight line, as you will see. Here you might have many structures. So these are extremely difficult to figure out experimentally because of the scale. So you have to have some program which can give you what it looks like at the nanoscale. So this is the start of OOMMF. So this is, I have shown you a slice which is from one of my simulations that I did many years back. That was the only image that I could find in my laptop. So, for example, these are often 1 to 2 microns in X direction, and 1 to 2 microns in the Y direction, and 1 to 100 nanometers thick. So these are roughly the element sizes that you can simulate using OOMMF. In your laptop, doing a 1 to 2 micron might be a bit challenging. Your laptop might start working very hard, it can overheat, it can stop. So you can, instead of doing 1 or 2 microns, you can do 100 nanometers by, say, 100 nanometers with the thickness of 1 or 10 nanometers. That will be fast. So OOMMF is trying to solve that. What happens to the OOMMF is trying to calculate the dipolar interaction, the exchange interaction, the Zeeman, and the spin orbit, if the spin orbit is present, and trying to find the energy minimum. So if you remember that figure that I shown you in the first slide, where it has a minimum, the ball rolling down the hill, the OOMMF is trying to find where the ball is, whether it's in one of the hills or one of the valleys. How does it do that? What OOMMF does is it breaks up this whole structure into tiny little cells. You can define the dimension of the cell. I'll show you in a second how to do that. So you just define these tiny little cells. Imagine those cells are 5 nanometers by 5 nanometers by 1 nanometer. So it's a tiny little cube of volume you define. And you assume that the magnetization is constant in that tiny volume. So that's the assumption that OOMMF makes. But it can change from one cube to the next cube. So the OOMMF, what it does is that it assumes that in this tiny little cube, it has an uniform magnetization. In the next cube, it has an uniform magnetization. But from this cube to this cube, the arrows may not be pointing in the same direction. How does it know where to point? It then calculates the energy minimum using these 4 interactions. So that's how OOMMF works. So this is known as a continuum approximation. In continuum approximation, we assume that you can break down the whole material into tiny little sections where you can assume that the magnetization is constant. Now you might come back and say that, well, the magnetization may not be constant. It's true, the magnetization may not be constant, but usually within a scale of 5 nanometers, the magnetization is constant. And the reason is the exchange interaction. When you go down to really small scales, this is the strongest interaction. It will align everything parallel. If anybody tries to align slightly in a different direction, that will cost a huge amount of energy. So dipolar interactions, they don't get any grounds. They don't have any voice. They're the weakest person in the room when it is 5 nanometers. But when it is 1 or 2 microns, then dipolar interactions can be stronger. It can overcome exchange interaction in larger length scales, not in smaller length scales. Okay, so this is roughly the the idea of OOMMF, that it is going to solve this. And now how it is going to do that, I think that's the end of this slide. So yes, how it's going to do that, I'll show you. But for that, I need to share a different window. Let me see how I do that. I'll stop presenting for a second. And I'll say present now. I'll present my entire Let me see. Okay. Can you now see a second window?
Yes.
Can you? Okay.
Yeah,
Oh,
yeah,
so
yeah.
you can see the sand dune, right?
Yeah. Yeah.
Okay, right, good, thanks. So I have logged into my office computer, where I will tell you how to do this. Okay, the first thing is you can install OOMMF. Installing OOMMF is very simple. If you're using a Windows device, it's really simple. So you Google OOMMF. So this is for setting up the whole thing. So you Google OOMMF. You go to the first website, Object Oriented Micromagnetic Framework. You go to software. There are alpha and beta releases. I recommend using the alpha releases. So you click on alpha release. It takes you to the recent version of OOMMF. So the most recent version was released on 8th of June. And the beauty of OOMMF, by the way, it's completely free. So you can download, you can do whatever you like. And if you have any problems, you can write to the guy who wrote OOMMF, Mike Donahue. He's a very nice guy. He usually responds very quickly. But I just warn you that first read the documentation properly before emailing him. So don't just go and email him, because he's usually a very busy guy. So anyway, so here, either this release or this release, whichever you want. I usually go with the second one, because usually the first ones have some bugs in it, and it might cause some problems. So in order to download this, you simply click this for Windows, and for Mac you have to click the source only file. So let me first discuss the Windows. So you go and click on this. This will download this is, so I won't be able to show you the Windows version. But if you click on this, it will download a folder, and from there you can click on OOMMF and you can install OOMMF. But before installing OOMMF, you need to install a language called the TCL-TK, or this is known as TCL-TIC. So for TCL-TIC, you can simply go to Google and you can say active TCL download, or you can simply say TCL download. Either of them will work. And in the TCL download, you go to this website called Active TCL. You might need to open an account. It's very simple. It's just your name and email ID. You open an account, you download the Active TCL. I won't be able to show you here because this is a Mac system. I won't be able to download it. You can download and then simply click on the .exe file. It will install by itself. And after you have installed the TCL platform, you then go to OOMMF, you download this OOMMF, and the OOMMF will automatically know that you have downloaded the TCL-TK platform. What is the TCL-TK or the TCL-TIC platform? So OOMMF is written in C++, but the TCL-TIC platform communicates with the OOMMF and the user interface. So the computer needs to know how to communicate, and that dictionary is provided by the TCL-TK language. So anyway, after you have downloaded, you will get a folder like this, and you can simply go to that folder and click OOMMF to start. And I'll show you how in a second. So that is how you download it in Windows. It's very simple. You can actually go to YouTube and you can say OOMMF Windows installation. And I think Mike Donahue, in fact, has a tutorial on OOMMF. So let's see. Let's go to YouTube. Where he explains everything. So there you go. So it has a tutorial. So you can see how you install. You can get more details on this tutorial. So my intention was to show you how to start OOMMF. So so that's your Windows installation. For Mac, it's a slightly more complicated installation because you need to download the source file. You need to download the TCL-TIC or the TCL-TIC package for Mac. Then you need Xcode in order to integrate the two, in order to communicate. But everything is given here. All the details have been given in the website, that how you do it for Mac. There is another simpler way, and I would suggest that you can do that initially. That is, you go to NanoHub. There's a website called nanohub.org. You can open an account. It's very simple. It's just your name and email ID and your university. You go there and you open an account, and from NanoHub, you can run OOMMF without even installing OOMMF. So when you open the account in NanoHub, this is what you see. So this is your profile. So you can go to the dashboard. That's your dashboard profile. So you click on dashboard. So that's your profile. And I think I've locked myself out. Yes, of course. So you can sign in with your Google account. Okay, yes. So when you go to your dashboard, you will see that there is something called a My Tools. In My Tools, go to All Tools. And you can simply search for OOMMF. And you will get many versions of this. You can run OOMMF on Python as well. But you choose the last one. Last one, you double click. And then you go to Launch Tool. You just simply launch. And it will open up a screen. And in this screen, in a second, you will see something appearing here. You put a tick mark here, it opens up. It puts another tick mark here, it opens up the OOMMF console.
Niladri, can you please make it in a full screen mode, because otherwise it's too small.
Right.
Okay.
Yeah. This one you mean, this right? Is this visible now?
Yeah, better than
now?
Before. Yeah, now it's okay. Yeah.
Now it's okay? Yeah, okay,
yeah.
Good. So I'll go back. So yes, so this was the initial starting point. So you click on this NanoHub, then NanoHub your account, it will open up. And I'll show you from this position how you deal it, but I'll not do it in NanoHub. I'll do it in my OOMMF here. So once you have installed OOMMF, this is a folder that you will get. So I'll minimize this for a second. So you can do everything from NanoHub, but I'll do everything in this computer. So in Windows, if you go, you will see that this OOMMF folder, and in OOMMF you will have a thing called oomph.tcl. You have to click the oomph.tcl and you will get that console. But here in Mac, we have to do it from the terminal. So we'll go to terminal. So you just simply type, you go to the TCL, sorry, you go to the, sorry, you have to change directory to the desktop. Then you go to the OOMMF folder. Then you type TCL shell. You may not be able to see.
Niladri, again interrupting
yes.
you. Just make it a bit bigger. Yeah.
Is this visible now?
Font size is small.
Not sure how you change
to make it a bit blurred?
This is actually not, this won't be relevant for Windows users anyway.
Okay,
but, so
fine. Okay.
And this, everything is given in the website. So what you do, I can send you an email of what to type, if that will help. You can send it to all the part. Yeah. So this is let me see. Can I scale that? No. So what you do is you change the directory. You go to the OOMMF directory. In the OOMMF directory, you have to type tclsh space OOMMF.tcl. So you go to the TCL shell and then you type the oomph.tcl. That's in Mac. So after you have done that, you see that this appears. There's a small icon, this one appears, and I will maximize this so everybody can see. You click on here. You click on here. And this is a console that opens up. Okay? And once it opens up the console, you need to start something which will ask the OOMMF to simulate. Okay? So that will be Oxy. Is this visible? This is the last one. The last option here.
Yeah.
Yes, sir.
Okay.
Yes.
Okay. So you just click on the last option, Oxy, and you will it will ask you to tick on this box. You tick on this box and the OXI will open. So this is the problem solver. This solves the problem, right? So, okay, and then you go to OXI, you can load the problem. But before loading the problem, we have to open a window where we can visualize. So we open display. So this is a display window. We won't bother about it now. So let's go back to the OXI. Sorry, I have to minimize this too. So this is your OXI one, which actually solves the problem. So in OXI, you go to File, and then you load. The path where you can go to your actual program is APP. The first one is APP. You may not be able to see it in Google Meet, but the first one is APP. You click on APP, scroll down. The last but one is OXS. You go to OXS, and then there are examples. So this is the example. You click on example, and you will see that it opens up a lot of files here. So these are pre-written files you can simulate. So let's choose a file called spin valve, since we know the spin valve now. We double click on spin valve. Okay, now it opens up output. So it can give you lots of outputs. What are we looking for? We are looking for magnetization. It will ask you, where do I want to put the magnetization? You want to put it in display. So you click on display. So now the program knows that the output magnetization has to be shown on the display too. And it will ask you every stage or every step. Tomorrow I'll explain you what is a stage and a step. For now, I'll click on every step. And I will click send. And you will see that in the display window, it has now sent a picture of the spin valve. So this is the first magnetic layer. You see all the spins. This is the copper layer in the middle. It has no spins. It is a third magnetic layer. You can color them. I'll go through it one by one tomorrow, so that we don't have to worry about it. You can configure. I'll just show you how it works for just the next 2 minutes, and then I'll stop for today. So you click on pixel, you apply, which means that the right magnetic field, if the moments are pointing right, it gets a red color. If they're pointing left, it gets a blue color. So this is what it looks like. And then you go back to OXI and you say run. You can run the program, you can stop, you can pause here. So if you say run, you will see that now you see that the spins have started to change direction because the magnetic field is reversing. And this is exactly what we were talking about, that it is not intuitive. You see that it is not pointing in the same direction. The spins near the interface starts to rotate. And you see that the counter here at the top is running the number of cycles. And now you see that it has started to change. It almost looks like an S-shaped, because you're reducing the magnetic field, and you reduce it a bit more, and you'll see it's, I hope I'll be able to show you the reversal. I'm not sure. It might take a while. But you see that it is non-uniform now. And the reason it is non-uniform, near the edges, the dipolar interaction is dominating, the north-south alignment, and in the middle, the extend interaction is dominating. So you have different regions dominating, and you have different interactions. Okay, so I'll stop here. We can do this run of the OOMMF tomorrow. So in the meantime, what you can do is you can open an account in NanoHub, or you can try to install the OOMMF in your Windows or in your Mac. If it is Windows, it's very straightforward. You can do it literally in just 20 minutes. It takes a bit of time to install the TCL/TK language, depending on your internet connection. So once that's done, running OOMMF is very simple. So if you if you can't manage to install it in Windows, you can open an account in NanoHub, and you just see that whether you can find OOMMF. If everything works well, tomorrow we will simulate a couple of things, and I will show you what are the important points in the program file, how to see them, how to change them. I think that's more or less what I wanted to say for today. Sorry, I've taken five more minutes.
It's okay. There is one question that if we make a system that a bunch of photons are decayed into bunch of entangled positrons and electrons, and they enters into the up magnetic field, what will be the spin direction of the particles?
So, okay, right. Sorry, could you repeat that, because it's not directly related to magnetism. Yeah, sorry, go on.
If we make a system that a bunch of photons are decayed into bunch of entangled positrons and electrons, and they enters into the up magnetic field, what will be the spin direction of the particles?
Okay, I don't know that whether I understood this question properly, because I am assuming that by spin direction of the particles, you mean both the positrons and the electrons, hopefully.
Probably.
But I would be honest here, I don't know the answer. I think I'm not qualified to answer this question, because there is entanglement involved. So if I say that it will be pointing in the same direction as a magnetic field and the positrons will be pointing in the opposite direction, it may not be as straightforward as possible. I need to think. So yeah, in short, I don't know.
Okay, just one thing about OOMMF is that, is it available for Linux or like Debian?
Yes, it is. And if you go to YouTube, you will be able to find how to install it in Linux. So if you just say OOMMF installation Linux, you'll get a video on how it's done.
Okay, thank you. That's all. No more questions here.
Okay, good. So tomorrow, if you can then download or at least open an account in NanoHub.
Just a minute. Another question pop up. Just suppose we have not applied any field to a simple magnet. Out of dipolar and exchange interaction, which one will be dominant? And how it depends on temperature and size of the sample. Also explain which one will be dominant when a field is applied.
Okay, so I'm assuming by when you mean that you have applied no field, is you have heated the sample, you have gone into a paramagnetic state and then cooled it down. I'm assuming that's what you mean by not applying a field, because otherwise it will remember whatever field you applied last time, even if it was like 1 year back. So if you cool the sample, it will spontaneously break up into domains, because it's a second order phase transition, it breaks up into domains. So, and the domains will be pointing in different directions. So if you look in between two domains, so one domain interacting with the other, the main interaction will be dipolar interaction. But if you look inside the domain, between electron spins, the main interaction will be the exchange interaction. Now, if you apply a field, the domains are going to align in the direction of the field, assuming there are no other complications. So the domains are going to realign in the direction of the field, and this is the combination of a dipolar interaction and the Zeeman interaction. Because the Zeeman interaction is the interaction with the external field, where it will try to align all the moments, and the dipolar interaction is the interaction between the grains, the magnetic domains, which will try to align all the magnetic moments in the same direction. So this is a fight, sorry, in the opposite direction. So this will be a fighting between the Zeeman and the dipolar interaction. The exchange interaction, by the way, is in the background. It's still there. It's not that it's not there, but it's the strongest interaction. It has aligned all the spins. So it depends on which scale you're looking at. If you're looking at larger scales of tens of nanometers, microns, it is a dipolar interaction. That's the dominant thing that dictates the magnetic state. What was the question about the temperature?
Yeah, how it depends on temperature and size of the sample. But if there is no field applied, then out of dipolar and exchange, which one will be dominant? And how will it depends on the temperature and size of the sample?
Okay, so if you increase the temperature, if you move more towards the Curie temperature, the exchange interaction will get weaker. So will the dipolar interaction. And in terms of the size, as I have discussed, that if it is a very small size magnet of micron, submicron, then dipolar interaction will be dominant together with exchange interaction. So that will determine the energy minimum.
Okay.
I hope I have answered the
Thank you.
question. Yeah.
Yeah, I hope so.
Any more
And there is
questions
no
from
more
the
questions, so yeah.
No, then I'll
Yeah.
invite Mrs. Swarnalekha Bandyopadhyay from our department to say a few words.
Am I audible?
Yeah.
Am I audible?
Hi, Swarnalekha ji, shuru karo.
Yes, Swarnalekha di. Yeah, you can
On
continue.
behalf of organizing committee, I thank Dr. S. Dugre for his wonderful introduction to Arduino and its application, which is useful to both faculty and students as it is introduced newly in the CBCS curriculum. And I'm looking forward for next day's presentation. I would like to thank Dr. Niladri Banerjee for marvelous presentation of micromagnetism and object-oriented micromagnetic framework, which motivates students studying advanced level in this field. I also thank our departmental teacher, Dr. Shubhendu Chandra, for nice demonstration of some virtual electrical and electronic experiments, which is also beneficial in this COVID-19 pandemic situation. Thanks to all participants. We will meet tomorrow at 3 p.m. in the same link and same platform. Thank you.
Thank you, everyone. I think we shall end our session today.
Yeah, now that's all for today, I think. Yep. Organizers, please stay back a while. We have to talk about something. And participants, you may leave now. Thank you for attending the session. Hope to see you tomorrow.
সিঞ্জিনি দি তুমি রেকর্ডিংটা বন্ধ রাখতে পারো এবার।